브레인링크 행사를 이제 올 사람들 다 온 것 같아가지고 이제 시작하도록 하겠습니다. Hello everybody. Thank you for coming to today's event, BrainLink X Lab Day talk concert. I would like to express my great gratitude for the KOFT, Korean Federation of Science and Technology Society, for funding this program, and also all the participants from various countries and also from Korea. And my name is Jung Shin Yoon, and I'm an assistant professor of Incheon National University. And today I'm one of the organizers and moderators of this event. And for the talk, I will moderate this program. And after that, we will have a panel discussion. And Dr. Lee, another moderator and organizer, will take part. Will proceed the program. And before starting the program, I would like to introduce the speakers of today's event. And first, Professor Mauro Pasta. And could you give a big hand for him? And Professor Egbert Pigemeyer. And Dr. Moritz Hantel. And Professor Georg Gamweitner, and Dr. Peter Axmann, and Professor Naoki Yabuchi, and Professor Kazihiko Matsumoto. And before starting the talk, we would like to show you the introductory video that shows the main event, the organizer of this program, and also how BrainLink X Lab Days are organized, and also working on that. And could you please, yeah.
Amidst the world's rapidly accelerating changes and competition, what kind of future are you preparing for? We are chartering a path to the future through science and technology exchanges, bolstered by international cooperation. In this era, where scientific and technological competitiveness is directly linked to a nation's diplomacy and security, the power to overcome such challenges lies in international cooperation that fosters synergy through collective efforts, and from talents who will shape the forthcoming era. The scholars of the world are gathering in Korea. A platform that facilitates exchanges between Korean and international scholars, as well as between seasoned and emerging researchers, is taking shape. BrainLink X Lab Day, organized by the Korean Federation of Science and Technology Societies, aims to be a global hub of talent. By consistently enhancing and expanding the global talent network, we're laying the groundwork for a brighter future. By inviting global scholars, X Lab Day provides an opportunity for young Korean researchers to glean insights from the vast knowledge and experience of both Korean and international scholars, as well as to engage in collaborative research. BrainLink X Lab Day establishes a global science and technology network among overseas scholars and Korean researchers. And in 2022 and 2023, a total of 24 BrainLink X Lab Day sessions were held in each technical field, with 787 participants, including 161 from overseas and 626 from Korea, building a global human network. Also, talk concerts, one-day public seminars were held in collaboration with the 2 nights and 3 days of BrainLink X Lab Day to enrich their experience. Professor Luke Pyeongse Lee of Harvard Medical School, Professor Ji-Won Kim of MIT, Professor Andrew Goodwin of University of Oxford. Emeritus Professor Teruo Okano of Tokyo Women's Medical University. Jeffrey Newmark of NASA Goddard Space Flight Center, Research Astrophysics. And Professor Dan I. Anderson of Uppsala University. The discussions will span 12 national strategic technology fields, pivotal to Korea's advancement, including the 3 game changers: quantum mechanics, nuclear technology, and AI. The event will see the participation of 40 Korean and international scientists and engineers. With 2 organizers leading each technical segment, the gathering will foster in-depth academic exchanges, encompassing the sharing of recent trends and information in core technology fields, in-depth discussions on research findings, and the sharing of ideas. And talk concerts will be held in collaboration with all BrainLink XLab Day sessions. The focus of XLab Day is connectivity and sustainability. Following the event, communities and clubs will be established based on each XLab Day session to ensure ongoing dialogue among attendees and promote collaborative research. COAST supports the reinforcement and expansion of the networks established through XLab Day. COAST, the organizer of XLab Day, stands as a beacon for Korea's science and technology society. Established in 1966, its mission has been to safeguard and amplify the rights and interests of scientists and engineers. Our endeavors extend to enhancing the public's grasp of science and technology and furthering its development through comprehensive policy research, planning, surveys, and consultations. As Korea's largest science and technology network with over 600 affiliated organizations, we are committed to promoting domestic and international cooperation and exchange. In the transformative era of the 4th Industrial Revolution, where science and technology spearhead groundbreaking challenges, COAST remains dedicated to its role as a facilitator of scientific and technological innovations.
안녕하십니까. 한국과학기술단체 총연합회 회장 이태식입니다. 과총은 사회 참여 확대와 권익신장을 도모하기 위해서 1966년 설립한 공익법인으로서 과학기술단체 육성 지원과 다양한 정책 연구, 기획, 조사, 자문을 통해 과학기술 발전에 기여하고 있습니다. 저는 2023년 과총회장으로 취임하여 새로운 도약을 위한 비전 프라이드 코스를 선언하였으며 이를 실현하기 위한 운영 목표와 추진 전략을 중심으로 빛나는 100년을 향해 모든 역량을 집중해 나가고 있습니다. 더 나아가 우리나라가 미래 핵심 기술 분야를 선도하는 기술 주권 국가로 자리매김하도록 국가적인 원팀 플레이를 이루는 데 있어 강력한 조력자가 되겠습니다. 대단히 감사합니다.
BrainLink XLab Day aims to broaden both domestic and international talent networks and become a global hub of talent. By making XLab Day into an event that scientists and engineers worldwide eagerly join, we intend to elevate Korea's global standing and bolster national competitiveness. Global Talent Hub, BrainLink XLab Day.
Yeah, thank you for watching the video. And before starting the main program, we would like to show you a slide, the QR code. So you can use this QR code to make some questions for the panel discussion and so on. You can already, if you take a picture of this QR code, then you can write some question on that. Then in the panel discussion and Q&A corner, then we will use these questions for further discussions. 조금 더. 네. Okay, I believe the audience already take a picture. Then now we move on the main program. And actually we have some changes in the timetable. And the first speaker will be the Professor Mauro Pasta. And the second will be Professor Georg Gambeitner. So please welcome the Professor Mauro Pasta.
All right. Thank you very much for the intro, and thank you for organizing this event. I know it's a lot of work, so really pleasure to be here, to be back to Korea. Today I would like to talk to you about solid-state batteries, hopefully tell you why this is one of the most promising beyond lithium-ion battery chemistries, but also highlight some of the challenges that we still need to tackle and understand from a fundamental scientific point of view. Before doing so, I would like to set the scene briefly. As I'm sure you know, we are in the midst of an electric revolution, and I would like to add we're finally in the midst of an electric revolution. I say finally because it's one of our best tools to tackle the problems associated with carbon dioxide emissions and global warming. At the core of this revolution, there is definitely the lithium-ion battery chemistry that was introduced commercially in 1991 by Sony in response to a need from the market. So back then, portable electronics were becoming ubiquitous, so there was a need for a novel battery chemistry that could store more energy in a smaller and smaller space. So we call this metric energy density, and it's expressed in watt-hours per liter. The number one driver of the lithium-ion battery market right now are electric vehicles, where energy density is definitely important because it directly corresponds to a range. EVs have been around for quite a while, but there wasn't a battery chemistry that would store enough energy to make their range competitive with the range of an internal combustion engine car. So definitely energy density, but at a cost. So if we want to increase the penetration of EVs in the market, we want this cost to be as low as possible, cost expressed in dollars per kilowatt hour. So a cost per unit energy. Now, these electric vehicles are only as green as the energy that we use to power them. So what we want to do is to increase the penetration of renewable energy, but as I'm sure you know, they are very intermittent in nature. So what you want is some sort of grid-scale storage that can smooth this power output. And the metric there is cost, but mostly levelized cost. So cost per kilowatt hour, per cycle, or per calendar life. So you want this battery chemistry to last for as long as possible, so you can depreciate them as much as possible. That won't impact the cost of your energy as much. And finally, there are novel applications such as the electrification of flight, where the metric is also different. So you want specific energy in watt-hours per kilogram, which corresponds to a nautical range, so how far you can fly your electric plane, let's say. So now the fundamental question here is, will lithium-ion alone be able to drive this electric revolution to its full extent? There are concerns about cost, there are concerns about availability and supply chain of raw materials, there are concerns about performance as well, and in particular concerns about energy density. So the energy density of lithium-ion batteries has been growing quite a bit, but the fundamental chemistry hasn't really been changed that much. We're still relying on intercalation chemistry, which is the same chemistry that was introduced in 1991. We're now approaching a physical chemical limit. There is so much that you can do on the engineering side. So we're basically reaching a plateau, a ceiling of this energy density. So if we want to go to the next level, next step, we need to change the way we think about how we store energy in a battery system. So a complete paradigm shift. So for the past 30 years, again, we use what I like to refer to as a stable host structure. So where your active material doesn't really contribute to storing energy, they provide a scaffold for lithium ions to be intercalating reversibly. So graphite as a negative electrode, a transition metal oxide or a phosphate as a cathode material with a liquid electrolyte in between. If you want to go to the next level, you need to change this concept to what I call reactive host structure. So you can get 3 to 10 times higher capacity by doing so. Examples are alloy anodes. Metallic lithium is the ultimate negative electrode. That will be the focus of my presentation today. Silicon, for example. If you pair lithium with sulfur, you have lithium-sulfur chemistry. If you pair it with oxygen, lithium-air chemistry. You can use a conversion cathodes. The real fundamental challenge here is that there are a completely new set of problems that we need to tackle when we move to this different system. We have significant bond breaking when you charge and discharge. Your host atoms do move. You have structural changes and rearrangements. You have substantial volume changes. And therefore, the new field in the past 10 to 15 years become quite prominent and important is the field of electrochem-mechanics. So electrochemistry, chemistry, and mechanics together to understand mechanism of conversion as well as degradation mechanisms that are affecting both problems at the atomic level with reversibility, at the particle level, fracture of the particle, SEI formation, new phases forming, as well as the electron level with expansion, breaking, and contact retention. Now, the prototypical material of this class of beyond lithium-ion chemistry batteries systems is metallic lithium. Metallic lithium is common in most of the beyond lithium-ion chemistry that I mentioned earlier. And the reason why is explained in this little table. So it's a BCC metal, it's the lightest metal, about 7 grams per mole. Standard reduction potential is the lowest, so the combination of both results into very high specific capacity, about 10 times higher than the capacity of graphite. Also, a very important property is this melting point that is only 180.5 degrees Celsius, and that's influencing and affecting quite a bit the mechanical properties of lithium itself, and we'll talk about mechanical properties in a few slides. Now, why would you want to implement metallic lithium? It's quite simple. That's a schematic of a conventional lithium ion. You have your transition metal oxide, for example, cathode, your separator in between, and your graphite porous electrode as a negative electrode. Here's an approximation of energy density where we're at right now, more or less at the same cell level. So by replacing graphite with the same cathode, same porosity, same everything, with a lithium metal foil and realistic assumptions, you can gain about 50% energy volumetrically and gravimetrically. So it's a big step change for where we're at right now in terms of energy density compared to normal lithium ion. And if you push this concept to the limit and you operate in a lithium-less configuration, so you're plating lithium on the first cycle, you can gain some more in terms of volumetric energy density, not as much gravimetrically as lithium is quite light. So now the question is, why aren't we doing this in a liquid electrolyte? Well, the problem is lithium doesn't like to plate uniformly. So if you try to plate at high current density, you enter this diffusion limited regime where dendrites are forming. Dendrites are filaments of lithium that are mechanically strong enough to pierce through your separator and short circuit your battery. And that's a recipe for disaster in a lithium-ion battery, as you have a flammable organic electrolyte. If the temperature increases, you also have problems of oxygen release on the cathode side that often leads to not only dendrites and short circuit, but also to catastrophic failure. You can, in principle, operate at lower current densities. You can charge a lower current density. You can do that, for example, in some of the aviation applications that I mentioned earlier. But still, even if you charge at a lower current density, you're often in this reaction limited regime where high surface area lithium, which is often referred to as mossy lithium, so not necessarily dendrite, but high surface area lithium, still form. And that leads to new lithium surface being exposed with the formation of new SEI, low Coulombic efficiency, you consume electrolyte, and ultimately you limit your cycle life. Arguably, one of the biggest motivations to move towards a solid-state configuration is to implement metallic lithium and its advantages from an energy density perspective. So what is a solid-state battery? It's actually quite simple. You're replacing the liquid electrolyte that I mentioned earlier with the solid. There are different kinds of solid. It could be a polymer. We focus our attention on inorganic ceramic solid electrolytes, and in particular sulfide solid electrolytes, as they have the mechanical properties required in principle to stop dendrites from propagating and forming. Also because they have a conductivity that is comparable, let's say, with a liquid electrolyte or even superior. And the combination of both result into potential increases in energy density, but not only. Other advantages of solid-state batteries lie in the fact that in an inorganic ceramic solid electrolyte, in principle, only lithium ions can move, and therefore you don't have the concentration gradients that I showed you earlier, so you could in principle charge faster. So this metric is called a transference number, is the fraction of current that is carried by your lithium ion, and it's close to 1. On top of that, you can also replace your liquid flammable electrolyte with an organic ceramic, and therefore you can have advantages also in terms of safety. Now, turns out that even in the case of a solid electrolyte, you do form something that looks like a dendrite, even if it's not a dendrite. So you do have catastrophic failure even in a solid. This is due to the formation of filaments of lithium that still propagate to your solid electrolyte and short circuit. They are often referred to still as dendrites, but are not necessarily dendrites. Their outcome is quite similar, so they lead to short circuiting. So I've been lucky enough to lead a project since 2018 called SOLBAT in the UK. SOLBAT stands for Solid State Metal Anode Batteries. We have a quite diverse team of researchers across multiple institutions in the UK to tackle these fundamental problems that are hindering the implementation of solid-state batteries at scale. So this project is funded by the Faraday Institution, which is an institution in the UK that focuses on fundamental research. The UK government is pushing quite a bit the green agenda and also battery development in the UK. So the Faraday Institution is the research branch of a bigger Faraday Battery Challenge, which is focusing on understanding as well as early stage commercialization. We divided these problems in a solid-state battery in 3 main areas. Problems on the anode side, which will be the focus of what I will discuss in a second. Problem on the cathode side, mostly associated with contact retention, volume change, and applied pressure. And problems on the electrolyte side, with a heavy characterization and modeling activity in support of these 3 work packages. Now, these are not separate work packages, like in the case of lithium-ion and liquid electrolytes. There's a lot of crosstalk. So problems on the lithium side and electrolyte side, as you will see in my presentation in a second, are quite tightly linked. Now, let's focus on the challenge of metallic lithium in this system. The whole community, and I think we contributed quite a bit to SOLBAT's project, now has a better understanding of what's going on in a solid-state battery at the lithium solid electrolyte interface. So we know as during stripping on discharge, you have the formation of voids at the interface between lithium and solid electrolytes. The origin of this void formation is found in the mismatch between the flux of lithium ion through your solid electrolyte and the flux of lithium atoms within lithium. And I'll discuss that in a second. So if you have a mismatch between the 2 fluxes, you end up in principle with the formation of vacancies that can grow in size, coalesce, and form a void. On plating on charge, the challenges are mostly mechanical, in the sense that mechanical degradation leads to cracking of your solid electrolyte that is then backfilled by metallic lithium, resulting in short circuiting. So these 2 phenomena are quite correlated, as if you increase voids, your current density is effectively increasing, and also this area provide a nice triple point, let's say, where you have access to space, ions, and electrons for mechanical degradation to occur. So you want to make sure that you prevent voids to start with, and then you can also tackle the problems occurring on plating or charge. Now, what does transport of lithium within lithium means? Well, you have 2 main mechanisms. One is vacancy diffusion, I think we should all familiar with. We characterize this diffusivity in quite a level of detail. We use a couple of different techniques. This is a PFIB SIMS experiment, secondary ion mass spectrometry. So if you put in contact a lithium-6 foil of lithium with lithium-7, and you then cross-section it, and you use the lithium-6 as a tracer, you can, if you record the time, visualize this concentration gradient, modeling with Fick's law, and get the diffusivity out. And we get a value of 1.25 10 to the minus 10 centimeters squared per second. Then we also cross-validated with solid-state NMR, again, lithium-6 solid-state NMR, mostly because lithium-7 is quadrupolar and diffusivity is quite low. So that helped us, building this activation energy line and therefore extract diffusivity as a function of temperature. So you can rely on diffusivity, vacancy diffusivities, or in the case of lithium, you can also rely on its mechanical properties. So as I mentioned earlier, the melting point is quite low. Lithium is quite soft, so its yield strength, so the stress they need to apply to plastically deform your lithium, so to really deform it, is quite low. It's in the order of 700 to 800 kilopascal. So you can basically squash it by applying pressure and therefore maintain contact that way. Also at room temperature, because of the low melting point, you also have quite a substantial creep, which is a permanent deformation of a metal when it's subject to a stress. So in normal metal, you apply stress and the strain will go to zero quite rapidly. In the case of lithium at room temperature, when you apply that stress, lithium keeps flowing, basically. So you can rely on pressure and temperature to maintain the contact. The other thing that is important to notice is the interface, and in particular the interfacial properties between metallic lithium and your solid electrolyte. In particular, the work of adhesion. So if you remember what I mentioned earlier, in an idealized system, you need to create a vacancy to start with to then generate a void. So if the work of adhesion is higher, then it would be more and more difficult to create that vacancy and therefore to coalesce and form voids. So interfacial properties are also extremely important. Now, a key takeaway message, you can prevent voids from forming, so you can increase transport if you increase temperature or if you apply high pressure, and that's what most of academia actually does right now. You operate at pressures or temperature are not particularly compatible with a real world application. For example, you see pressures in the order of megapascals very often in solid-state batteries, and that's a no-go for an implementation into an actual pack. So we are working under the assumption that we need to decrease the pressure below 1 megapascal. And if you look through the literature, very few groups are actually working at this pressure, as the problems are quite severe. The same thing with temperature. Yes, you cannot increase the diffusivity by increasing temperature, but at the same time, we want to make sure that our battery pack operates temperature compatible to a lithium ion as well. So it could, in principle, it should, in principle, go down to the minus 30 that we need to use in our cars. Now, our approach to try to address some of these problems is to what I refer to as light alloying. Light doesn't necessarily mean weight. Light for us means a very small amount of a secondary phase or a secondary component that will allow you to modify the properties of lithium enough to try to address some of these problems without substantially affecting the energy density. So you don't want to add so much of the second component and that your energy density will be affected heavily. So we still want lithium to store charge as much as possible. And I'll give you an example today, is the lithium-magnesium system that we looked into for quite a good level of detail for a few years right now. And I think it's a very good model system and also a very practical system, as I'll show you in a second. So what's special about the lithium-magnesium system is the phase diagram. So you can see you can dissolve, let's say, quite a big amount of lithium in this system until you reach 70% lithium in magnesium, retaining the same BCC structure. So this is effectively a solid solution of lithium in magnesium. When you pass the 70%, you enter this alpha plus beta region, where you have this alpha HCP phase, hexagonal phase of magnesium. The diffusivity of lithium in this phase is very slow, and in particular, this alpha HCP is quite slow. So what we can do in-house, we can make our own alloys by melt solidification in an inert atmosphere, of course. We made 20, 10, 5, and also, as I'll show you in a second, even below 5. Atomic percentage lithium in magnesium in lithium. So you can melt them, solidify at different rates, and therefore have a certain level of control on microstructure. You can perform XRD, OCV measurements, and prove that you actually form what you wanted to do, but we do a quite substantial characterization. We characterize a microstructure. So you can microtome, so polish the surface of your lithium metal foil, and then characterize it using EBSD, for example, electron backscatter diffraction, that allows you to basically tell what these grains are and what's their crystallographic orientation. So all these different colors corresponds to a different crystallographic orientation of your crystal here. You can see that as you increase magnesium content, you are affecting a bit the crystallite size, but they're still quite big. They're in the orders of microns or millimeters in the case of lithium because of the very, very high diffusivity. We can then test the mechanical properties during indentation as a function of the crystallographic orientation. So one indent is maybe in the order of, let's say, 1 to 10 microns. You can perform several indents within a single crystallographic orientation and get the crystallographic orientation dependence of these mechanical properties. You can get hardness, for example, as a function of magnesium. You can get elastic property, plastic properties as well. You can characterize the interface formed between your alloy and the solid electrolyte. And you can do that by using electrochemical impedance spectroscopy in a 2-electrode, 3-electrode system. We can do XPS and characterize the chemical composition. And you can also measure the diffusivity as a function of what you're adding in there. And again, we're using solid-state NMR in here because it's quite convenient. You make your alloys, you use solid-state NMR with lithium-6, and you quite rapidly get diffusivity and activation energies that allows you to extrapolate on a different temperature range. Now, a couple of takeaway messages for this specific system. As you're adding more magnesium, your alloy becomes harder and the diffusivity is decreasing, which is exactly what you do not want from a transport point of view, but it's quite beneficial and helpful in terms of contact retention. So if you look on the right-hand side over here, you have lithium magnesium on top and your solid electrolyte, not particularly densified in this case. We'll talk about that in a second. As you strip the lithium away, the magnesium is left, and therefore it allows you to retain contact without the generation of the voids that I mentioned earlier. So now the fundamental problem here, if you look on the left-hand side, is to find a good compromise. If you see the curve, the line in black here, that's pure lithium. As you increase the pressure, you can rely on yielding and creep, and therefore increasing accessible capacity. So at high pressures, you get a lot of capacity out of your lithium, but it's a function of pressure. And at low pressures, the accessible capacity is quite low. The 5% magnesium in blue here, as you can see, you retain pretty much the same accessible capacity, so it's almost pressure independent, but at the same time, the accessible capacity that you get is not particularly high, and that's due to the fact that even 5% compromises diffusivity enough to then slow down your transport. So the whole concept that we would explore is to go even below 5%. So 1% magnesium is enough to help retaining contact, while at the same time to be less pressure dependence and access quite a bit of capacity even at low pressures. Yes, this helps with contact retention and voiding. We're still working right now on trying to increase transport within lithium itself by looking at secondary phases, secondary components, and it's something that hopefully we'll publish soon. Now, few words on what is actually happening during plating or charge. There was a bit of a debate for a few years on what was actually happening there. If the filaments that I mentioned earlier were caused by lithium itself, trying to plate within your solid electrolyte, or a mechanical degradation. I think there's quite a bit of agreement right now in the community, in particular in the sulfate system, that the first thing that actually happens is mechanical degradation, which leads to the formation of dendrites, cracks that are then backfilled by your lithium. So mechanical degradation comes first, and then your lithium metal basically penetrates through during plating. And I think we have quite a bit of evidence of that. And you might argue, well, how is that possible that something as soft as lithium is actually able to open a crack? Well, a couple of things. First of all, and as mentioned in a second, very often these solid electrolytes are very hard to densify, so they're not fully dense. There's quite a bit of porosity in there, and that's affecting substantially their fracture toughness. They're not as tough as you would think they are, and therefore it's enough a lower stress that you would expect to open this crack. The second thing to consider is that any metal at a nanoscale, its hardness is a function of the size of your defect in here, because the number of dislocation is limited. So lithium gets quite hard at the nanoscale. So the combination of both the presence of defects and the mechanical properties of lithium do result in the opening of a crack that is then backfilled by your lithium. So what is the solution then? Well, if you can fully densify, that would be ideal. And we now have evidence. Left-hand side, you have an 83% dense solid electrolyte, densified by cold pressing at 400 megapascal, which is a very high pressure. But even in this condition, you see your solid electrolyte is quite porous, and it's enough, basically, 5 microns of plated lithium, 1 milliamp per hour per centimeter square, and a 1 milliamp per centimeter square current density to form a crack, and therefore shorting. While here on the right-hand side, 99% dense pellet obtained using spark plasma sintering. And as you can see, 9 milliamp per centimeter square on the right-hand side, 8 milliamp per hour per centimeter square plated, so 40 microns of lithium. And you still have your fully dense, no cracking, no short circuiting. Now the fundamental question is, how do we achieve this level of densities in something a little bit more pragmatic and practical, like a thin film separator? And that's a whole field of research that we're still carrying out and pursuing. You can tape cast quite thin solid electrolyte layers right now. It's not that difficult. If you add a tiny bit of a binder in there, you can tape cast it quite easily, below 50 microns. Quite flexible still because they're quite porous. But as you can see over here, even if you apply higher pressure, you do still retain quite a bit of porosity. So you do increase conductivity as you densify these films. You do increase engineering stress, but still the presence of all this porosity results in very low fracture toughness, and therefore they pretty much all short a very low critical current density still. So here again, understanding densification in detail and the whole science of densification will be critical. For those of you that are working in solid state, it's quite common to use warm isostatic pressing to fully densify. Well, this is one of the reasons, achieving full density in your solid electrolytes as well as in your cathode. One final slide, and then I will wrap up. Interfaces. Another thing that has been less characterized is what is actually happening at the interface between metallic lithium and a sulfide, solid electrolyte in particular. Turns out that this interface is quite reactive. People used to think, in particular in the presence of an argyrodite, that this interface would be self-passivating, so you will form some sort of an SEI, but the SEI will not propagate over time. We now have evidence this is actually not the case, and this interface keeps growing over time, so understanding it will be critical, and I will give a talk in a couple of days specifically on that and our understanding around interfaces. And with that, I would like to summarize briefly and say that solid state has a lot of potential. It could be the no-compromise chemistry that we're all looking for EV application. No compromise meaning it could be superior to lithium-ion from energy, power, as well as safety. And it could empower a vision when you have EVs fully equivalent to internal combustion engine cars in terms of range, charging time, as well as cost. There are still a lot of problems that need to be solved scientifically before we can implement solid state at scale in particular. And I would like to argue that the field of electrochemical mechanics is important. And for those of you, I see a lot of students here that want to enter this space, I think it's definitely my recommendation to look into this because it allows you to really tackle problems from a fundamental perspective and therefore potentially find solutions. And with that, I would like to thank you all for listening, thank all the funding sources, Faraday Institution in particular, the group. Thanks for listening. Happy to take any questions later, I guess, during the panel discussion. Thanks.
Thank you very much for your insightful presentation. And as he mentioned, we will have a Q&A and panel discussion session. And could you please show once more the QR code? Yeah, if you have any question, you can make a question using this QR code. Then you will access to a link, some web page. Then you can write your question, and we will discuss those questions in the Q&A sessions. And next, we will have a speaker, Professor Egbert Piegemeyer, and he's from Aachen University, and he will give a talk about the solid-state batteries for lithium-sulfur batteries. Sorry. Sorry. I am very sorry, yeah. Yeah, the second speaker is Professor Georg Gambeit.
Okay, you see we are perfectly flexible, but I think maybe we stay in this order. So first of all, thanks a lot for the organization of this event. I think it's a wonderful opportunity for me. It's the first time in Korea. And yeah, I'm happy to speak to you today. I think it made sense that we switched the talk with Mauro, however, because he told you already a lot of issues about solid-state batteries, which, let's say, I can skip. But actually, my talk for today is focused a bit more on the application. We are having a larger program on sustainable aviation at my university at Braunschweig, and I will give you quite a bit on background about this. Basically, however, we are developing solid-state lithium-sulfur batteries for this application, and I will also tell you why. So I think I can use this for switching. Yes. Yeah, this is the overview of my talk. Basically, why do we consider sustainable aviation? Of course, airborne mobility is a huge megatrend. We have about 4.5 billion passengers. This is the data of 2019. You know, then there was the COVID crisis, so everything got a bit, let's say, messed up. But nevertheless, we know that we are kind of back on track, and still aviation has a high growth. We have a doubling of the volume every 15 years approximately. It might change due to some tendencies, but still growth is really strong. Because of course we have lots of advantages of air travel. A lot of requirements that play a role here. The travel time, of course, interconnectivity, individuality, safety, and regulatory constraints, which of course for aviation are also highly critical. And to, let's say, meet these multiple goals, we need to have new technologies. Why do we need to look at sustainability here? You might think, well, aviation just still has a small impact. Basically, if we look today, then we might say that about 77% of CO2 emissions are from the stationary sector, about 23% from mobility. In this mobility sector, then we only have about 2% from aviation. However, actually, CO2 emissions at higher altitude have a stronger effect on the climate, which means that actually about 6% is the true climate effect. So already there, sustainability is more considerable. And of course, if we think about a scenario in 2050, then basically we might say, emanating from today's figures, that possibly the stationary energy sector has become zero emission. We might think that maybe 75% of the road transport is also zero emission. We'll see about the development. According to some plans we have, this is rather conservative, but nevertheless, of course, there might be still some old cars and trucks driving around. And here we basically assume that the other sectors grow similarly to aviation, which is actually a very conservative estimation. Of course, also especially the train sector will be fully electrified possibly by then. So, but anyhow, we see that the effect of aviation in this scenario is 48% of the CO2 emissions, so it becomes dominant. And this of course means that we need to think about making the aviation sector sustainable already today, because we also have a problem of a long life cycle, because of course the life cycle of an airplane is longer than for cars. And here you see some projections. Actually, the kind of yellow area, this is the COVID times, which of course showed some disruptions. These are neglected here for simplicity, but as I said, we can basically assume that the sector is growing again and it's back to the old figures. And with this projection, you see that we can do something with current technologies. Of course, we can make planes saving a bit more energy, but nevertheless, still you see a growth in the CO2 emissions. We can only get to a true decrease if we switch to novel technologies. And one reason for this is that also, of course, the fleet sizes will expand due to more and more passengers. And we have a technology life cycle which is longer than 40 years, meaning that today's fleet is actually rather based on older designs. We can say there is more or less a 2050 design type, which is now just, let's say, becoming stronger in the aviation field and is basically dominating the fleet still until the year 2050. And all new designs, these will be, let's say, the typical cycle is about 20 years for a new design type. So the newer ones here are 2035, and you see even in 2050, still the older designs have an equal share. So it takes a long time. Even if we think now about future airplane designs, then they will not be dominant until 2050. Of course, that's quite clear. Yeah, you have lots of regulations. Companies cannot just make a new airplane every year because there is a lot of certification, testing required, which of course is very expensive. And yeah, this basically means we need versatile technologies. We have to be, let's say, working fast on new technologies for airplanes. And at my university, we have started an excellence cluster, which we have been awarded 6 years ago. It's a large research cluster where we got funding of about 45 million euros, looking at all different aspects of sustainable aviation. This is about innovations and designs, about developing criteria for decision making in these scenarios. Of course, we're assessing the key questions for this research and technology, and we identify the game-changing technologies that we can transfer into aviation. So basically the cluster is composed of 3 different parts. We have a cluster area A, which is more on the air transport system, because of course also this can be made much more efficient. Also this needs to be changed when we switch to sustainable technologies. Then there is a cluster area B, which is more on, let's say, flight physics principles, designs of airplanes and vehicle systems. And the cluster area B, that's of course the one relevant for us here in the battery sector. This is about energy storage and conversion. Just a few examples. So here you see a novel design of such an aeroplane, because this might be much more suitable for example, a hydrogen-driven aeroplane. Then we have new systems of interoperability, new traffic management systems. We also need to electrify the aircraft. So in the future you need to switch, of course, from the turbine to electrified propulsion in the airplane. And we are investigating, of course, the batteries for these airplanes. What we have to say, however, is that there will be not one design that fits all needs. One has to see that there are, of course, highly different requirements. You see some very futuristic designs here. Yeah, this looks kind of funny. Well, we will see if we ever will see such an airplane. But there are very widespread demands for these airplanes. The mission profile is from less than 100 kilometers to more than 10,000. A very small airplane, 40 seats to 400. And of course, this means that for the energy storage and conversion technology, there are also very different demands. Then, of course, the cost of the energy that we use in this airplane is highly different, whether it's electric, whether it's liquid hydrogen, or whether these are bio or electro fuels. And also the airports will have to change. Yeah? There are different requirements for these different technologies. So of course, this will be a, let's say, rather versatile, and there will be different solutions that are developed. And also we have to see that, of course, it's not only about CO2 emissions. So basically, this is a figure that basically was developed in the European Initiative Flight Path 2050, where basically the goal is to have sustainable aviation brought forward. And we see that, of course, the CO2 emissions are an important aspect, where, of course, we want to go from the left to the right side to have less CO2 emissions in this figure, but also the non-CO2 emissions are important and they play a role. And basically we see that, of course, with the so-called SAFs, sustainable aviation fuels, so basically to have kerosene based on renewable resources, there we can reduce the CO2 emissions over the whole life cycle, but of course still hydrocarbons will be burnt, so you still have non-CO2 emissions. But even hydrogen combustion, even though we have basically the CO2 reduced to more or less zero, even there you have some nitric oxides, for example, that form during the combustion. So non-CO2 emissions are still there, and only a battery electric car would be kind of the gold standard, where both emissions are reduced to almost zero, whereas with a fuel cell we at least have water emissions that also might have some impact on weather and on climate. So here we see that batteries, of course, would be the most desirable, but with batteries we have a big problem. And this is, again, coming back to the energy density that Mauro had introduced. Well, basically, here we have the so-called volume or volumetric energy density and gravimetric energy density. Actually, to be more precise, this would be the specific energy, as Mauro called it. So energy that we can store related to volume or weight. And of course, we see this is a logarithmic plot that kerosene, gasoline, they are much higher than what we can store in batteries. This comparison is, of course, not entirely fair. On the one hand, we are comparing the pure substance that is burned to the whole system, where we reversibly shift the energy. But nevertheless, we see that we are orders of, or one order at least, 1.5 orders of magnitude below to what we actually have in kerosene. It's not fully what we need, because also the efficiency is not 100% for kerosene. But nevertheless, we see that we are not there with the batteries, especially taking into account that often what you find in the literature is a value for cell level. But of course, the battery has to be included in a larger module or in a pack, and all of these additional components, they will reduce the energy density. So we will see, or we do see, the lithium-ion battery that we have plotted here does not fulfill what we need for a battery-powered airplane. And if we compare different types, then we see, well, of course, we are closest to a smaller plane, only for a regional application. And this is, let's say, the one that appears realistic today. Nevertheless, we still have a gap that needs to be bridged. And of course, we see also that the big problem is with the specific energy or gravimetric energy density. Here we have the largest difference that needs to be spanned. So we need new battery technologies, and we decided to focus on the lithium-sulfur battery here, because for aviation it seems more attractive than the lithium-ion battery. So basically the volumetric energy density is quite good for a lithium-ion battery, but we have typically a weight problem. And for the lithium-sulfur battery, it's kind of the other way around. So yeah, you have a larger volume. Partially, this is also due to the lower density of sulfur, but we have a very attractive gravimetric energy density, because with sulfur we can store a lot of energy. The specific capacity is 1,670 milliamp hours per gram of this active material, whereas for a normal cathode material in a lithium-ion battery, we have 250 milliamp hours per gram. So here we are much higher. But we have some, let's say, compromises to make, as you see in the other numbers. And this, nevertheless, makes this lithium-sulfur battery highly attractive. Additionally, sulfur is abundant and cheap, and we basically get rid of these other metal components, these transition metal components, which, of course, for a life cycle assessment also is an attractive factor. But we have a number of disadvantages in a traditional lithium-sulfur battery with a liquid electrolyte. On the one hand, there is the dendrite formation on the lithium anode, as Mauro already mentioned, but we also have a so-called shuttle effect, because the sulfur has to react. It undergoes quite complex reactions, actually, and the so-called polysulfides, longer or shorter chain sulfur compounds that form during this cycle, they will reversibly go back and forth in the battery, and unfortunately they will deposit on the anode, form some insoluble compounds, and with this you lose capacity over the many charge and discharge cycles. So this is a problem, and well, what can we do about it? We have investigated a so-called artificial solid electrolyte interface. ACI was already mentioned by Mauro, and here we basically have a layer. We focus on polymers that we work with, which of course have the advantage that they are flexible, and typically they can form a very good interface to the anode. And in this case, we had a foil that is conductive to lithium ions that was simply pressed on the lithium foil that gave a much more stable and much more reproducible performance of batteries that we tested. Nevertheless, we see still some decrease over hundreds of cycles, which means that we still have some of this polysulfide shuttle in effect, which is then why we decided to go one step further to a true all-solid state lithium-sulfur battery, where basically we replaced the liquid electrolyte by a solid one, and we decided to again have a polymer as the electrolyte compound in this system. Ideally, then you have a number of advantages that you can combine. Of course, also for aviation, this is highly desirable because of safety aspects. The electrolyte cannot leak, it's non-flammable. But the big problem with the polymer is that it has a low ionic conductivity at room temperature. So there is a strong dependence on the temperature, and typically such batteries you always have to operate at higher temperatures so that they have a good conductivity and that they are efficient. Well, we designed a special type of polymer. I don't go into the details for the sake of time today. I will present that in more detail in the next days. And this is basically a flexible membrane formed from this polymer, which we can easily process. And basically by optimizing the composition of that polymer, we could already see that we have a good effect on the ionic conductivity. So here on the right-hand side, you see the PEO in the dark green points, where you see a strong temperature dependency, and at room temperature this is only low, 10 to the power of -5 Siemens per centimeter, and this means it's not sufficient for room temperature operation. Well, we combine it with the second compound, which is this PETA, where the pure compound has a very low ionic conductivity. But as we combine these two compounds, we get a system that has a much more stable ionic conductivity also over the different temperatures. And you see that with a system of 1 to 12 mixing between the PETA and ethylene glycol compounds or components, we have a 10-fold increase in the ionic conductivity. But that would not be sufficient. We have to add some other component, and here we decided to go to a hybrid solid electrolyte, where we additionally add ceramic particles, lithium lanthanum zirconium oxide. These you have to actually modify on their surface. That's why we call them FLLZO. This is a type of functionalization that we used. And you see then we again have a flexible system. If you incorporate the pure particles, it's very brittle and you cannot process it. But after the surface modification, it becomes flexible. And we again have a 10-fold increase in the ionic conductivity. So here the scale is changed, and from 10 to the -4, we increase to more than 10 to the power of -3 Siemens per centimeter at room temperature, and this is basically perfectly fine for an operation. And we could see that then we have a battery that we can operate at room temperature that has a performance similar to a liquid electrolyte, although here you see that the rate dependency is still quite strong, which actually is not due to the solid electrolyte, but due to the cathode configuration that we used in this system. Okay, well, I will talk about it more in detail in the next day's discussions. But for today, a short summary. So I hope I could show you that we need many technologies to have sustainable solutions for aviation. Battery-powered aircraft is one possibility that appears feasible for the short range, that kind of is the gold standard and has high promise. But of course, there are still some challenges that we face today. And for this application, lithium-sulfur batteries have high potential and appear highly attractive. And we combine that with a solid-state electrolyte for increasing the safety. And we can also implement, as I showed you, artificial solid electrolyte interface layers to also improve the performance of these batteries. I have to thank my research group, especially the three people shown here, Unju John, my former Korean PhD student who will also join us in the next days, and then Nico Grotkop and Annelies Jean-Fulcran. I have to thank the German Research Foundation for funding, and thank you for your attention.
Thank you very much for interesting talk and also the photo futuristic aircraft. And the next we'll have a talk of Professor Naoki Yabuchi, and he'll talk about the positive material for lithium-ion batteries.
Okay, thank you for my introduction, and thank you for the invitation to this interesting conference. I'm really happy to visit here. So this university is my second time to visit. So before COVID-19, I visited this university, and then I'm really happy to return to this university again here. So today's my talk is about nanostructure and practical high-capacity positive electrode materials for lithium-ion batteries. So now, the most important point about battery is how we can reduce its cost. And the most cost-expensive part is a positive electrode materials. And then historically, lithium-ion battery started from lithium cobalt oxide. Cobalt is, of course, very, very expensive elements. So to reduce the battery cost, so my former supervisor, when I was a PhD student, Professor Ozuku developed cobalt 1/3, nickel 1/3, manganese 1/3 system in 2000, so-called ternary system. And then now, cobalt content is reduced only 1/3 of original compositions. And then now, state-of-the-art electric vehicles uses lithium nickel-rich systems, for example, 10-1-1 system. So cobalt content is reduced to 10%. Then my first topic today is, can we make a pure nickel system without cobalt ions, cobalt-free pure lithium nickel oxide? So this is our publication about this topic. So first, let me show you stoichiometric lithium nickel oxide. So this sample is very difficult to manage. So always degradation is observed upon cycling. So here you can see typical charge and discharge curves for continuous 20 cycles here. So initial discharge capacity is very high, over 200 milliampere per gram. So however, you can see clear degradation upon cycling. So however, when you see differential capacity plot here, so very unique degradation process is observed. Only high voltage region here, so-called H2, H3 phase, I3 to H4 phase transition, high voltage region, only degradation is observed. And also lower voltage region, you cannot see any changes at a lower rate. So this is a very unique degradation process. So many people discuss about material fracture associated with volume changes. So in this case, is isolation of electrode materials results in more capacity loss for entire regions. However, this degradation process is very, very unique. Only high voltage region is observed. And also we discuss in detail about this application, about the origin of this degradation process. So in summary, so this caused by surface degradation, and also upon charging, nickel ion migrate to tetrahedral sites. So nickel ion cannot migrate back to tetrahedral sites after the accumulation of impedance at the surface. So to suppress these unfavorable phase transitions associated with the nickel migration, so we synthesize slightly lithium deficient lithium nickel oxide. So strategy is very, very simple, very easy. So we synthesize lithium nickel oxide with 4% lithium deficient conditions. Only difference is lithium content in the starting materials. Very simple strategy. So this is a synthesized samples. So we carefully analyzed cation distribution in these samples by using a synchrotron X-ray diffraction and also neutron diffraction study. And then our conclusion is now we have a 6% of a nickel ion in lithium layers, and also 4% of a lithium ion in the nickel layer. So this sample contains anti-side defects between lithium and nickel ions. And this anti-side effect is anti-side presence is very, very important to improve the reversibility of the samples. So, and also particle size is slightly smaller compared with as prepared stoichiometric samples. But essentially, this is a layer of materials. So here you can see comparison of a charge and discharge curves for stoichiometric lithium nickel oxide, lithium deficient nickel oxide. Reversible capacity is slightly lower for lithium deficient samples as you expected. So however, cyclability is much better. So after 30 cycles, capacity is larger, and also when you see high voltage region degradations, so now you can see much improved reversibility for high voltage region reversibility. So this is the results with a conventional electrolyte solution. So problem of a pure nickel system is actually surface degradation is very important. Therefore, selection of a electrolyte also very important parameters. So we use as a model electrolyte, so highly concentrated electrolyte solution with a lithium FSA. So this is reported by Professor Yamanada's group in 2016, so very old publications. So very simple combination of FSA and DMC. So however, concentration is very high, 5.5 molar. Viscosity is very high. This highly concentrated electrolyte solution is not wettable to conventional polyolefin separator without no polar functional groups. So in such case, typically we use the high porosity glass fiber filter like this. So this glass fiber filter is of course wettable to highly concentrated electrolyte solution with high viscosity. However, another problem is a dendritic growth of a metallic lithium results in internal short circuit. So therefore, it is difficult to use a highly concentrated electrolyte solution with for high areal capacities. So recently, we published one paper to energy advances here. So we found that meta-aramide coated polyolefin separator is wettable to highly concentrated electrolyte solution. So polyolefin separator shows a very small porosities, small pores. However, we have oxygen functional groups for aramide. So this oxygen presence is nicely improve our wettability to highly concentrated electrolyte solution with high viscosity. As a result, so reversibility is clearly improved. Sorry, reversibility for lithium nickel oxide stoichiometric sample with highly concentrated electrolyte solution is also clearly improved. So however, if you see high voltage regions, so degradation process is essentially same. So you can see increase in impedance at high voltage region, loss of reversible capacity for high voltage regions. However, for the case of lithium deficient samples, now reversibility is very, very good with a highly concentrated electrolyte solution because of improved surface participation stability. So now you can get a very high reversibility, so no capacity failing for 100 cycle tests. So this is a summary of our hypothesis for the improvement of anti-side defects. So stoichiometric lithium nickel oxide, after lithium removal, so nickel ion migrate to tetrahedral sites. So after that, so under coordinate oxygen is very, very chemically unstable. Therefore, easily reacts with an electrolyte solution, leading to a high impedance upon cycling. So, however, for the case of anti-side defect samples, now we have a small amount of a nickel ion in lithium layer. Therefore, if even after lithium removal, nickel ion cannot migrate to neighboring tetrahedral sites to these nickel ions because of repulsive electrostatic interactions. So, however, you may also notice such a presence of anti-side defects disturb lithium ion migration However, so particle size is clearly smaller compared with the stoichiometric samples. Therefore, increased surface area with a small amount of unchild defects, coupled with a very chemically stable, highly concentrated electrolyte solution, so we can improve our reversibility for pure lithium nickel oxide without cobalt ions. So this is a more recent our findings. So now we are trying to do a more heavier loading, 20 milligram loading. Areal capacity reaches 4 milliampere hour per square centimeter. So now concentrated electrolyte solution is a slightly different compositions. So but a lithium FSA based electrolyte solution. And also we have a very special carbons supplied by our collaborator 3DC. So-called graphene mesosponge. This one is a porous carbons, and also we have a very thin graphene layers. So this sample electric conductivity is a very high, and also porosity is a very high. So we can reduce the amount of additional carbon contents. Now we can add only 0.5% of carbon, conductive carbons, in our lithium nickel samples with 2% of a binder. So 97% of our loading. And also reversibility is very good at 1 over C rate. So no capacity failing for 20 cycles. So now, so this sample with a very high areal capacity with a possibly metallic lithium works well in the future for high energy metallic lithium with a pure nickel systems with high loading, with a high areal capacity. So now we are convincing our lithium deficient lithium nickel oxide is very, very attractive for practical applications. And then now our next target is pure manganese chemistry. So of course nickel is also, cobalt is very expensive, but nickel is also expensive elements. So we hopefully try to develop high performance, high energy manganese based electrode materials. And then we revisited so lithium manganese O2. In the past, many people tried to use this material for positive electrode materials, but no successful reports are found. And then recently, we found, so we reported some achievement, so research progress for lithium manganese O2 in these publications. So some dynamically stable phase over lithium manganese O2 is a so-called zigzag type layer structures. So however, and also this sample has many problems. So stoichiometric lithium manganese O2, so initial discharge capacity is not so high. Upon cycling, you can see increase in reversible capacity. So this is associated with a gradual phase transition into a spinel-like, low crystallinity spinel-like phases. So we carefully analyze the reaction mechanism of lithium manganese O2 with different lithium polymorphs in these publications. So please check our publication in detail. So finally, we found that so nanostructured lithium manganese O2 is a directly synthesized, very efficient methodology. So again, we have a very common chemical precursor. So manganese 2O3, very usual chemical, with a lithium hydroxide, heated at 700 degrees Celsius, only 0 hours, and then we cooled down to room temperature. Very simple strategy. So, however, we found that lithium manganese O2 is a single phase is obtained. So important point is the surface area is relatively large, 4.4 square meter per gram. And also now this 110 diffraction line is PEC is very broad. So this is because of a presence of stacking faults or domain structures. So some dynamically stable regions, zigzag type layer structure here, and also we have a straight type. So this structure is essentially the same with lithium cobalt oxide on lithium nickel oxide. So by optimizing our synthesis conditions, we have a low crystallinity, so domain structured lithium manganese O2. And also we still have a problem about a solubility problem for manganese ions. So we surface was coated by lithium phosphate. This is also very simple strategy. So this sample, nanostructured lithium manganese O2, can deliver large reversible capacity from initial cycles. So domain structure promotes a phase transition process. From initial cycles, we can get large reversible capacities. And also from second cycles, now this sample delivers over 220 milliampere per gram. So energy density reaches nearly 800 watt-hour per kilogram based on positive electrode materials, so which is competitive to lithium nickel oxide. So, however, problem is cycle life is still we cannot compete lithium nickel system. So cyclability is not good. So after 60 cycles, now you can see clear degradations. And also after cycling, we measure the XPS for metallic lithium. So this is because of a dissolution, capacity loss originates from a dissolution of manganese ions and also accumulation at a metallic lithium surface. So therefore you can detect the presence of manganese ions at the surface of a metallic lithium. So degradation clearly originates from a dissolution of manganese ions. Okay, again, electrolyte is important. Highly concentrated electrolyte solution clearly improves reversibility. So because of concentrated electrolyte solution, all of solvent is already solvated to lithium ions. We have no free solvents. Therefore, so highly concentrated electrolyte solution is effectively suppress manganese dissolution. Now cyclability is clearly improved and also better Coulombic efficiencies. Now we can achieve 90% of capacity retention even after 100 cycles with nanostructured lithium manganese O2 with a highly concentrated electrolyte solution. And also after 25 cycles, you cannot detect dissolution of manganese ions at metallic lithium surfaces. So, and also only problem for pure manganese system is discharge rate capability is so hopeless. So even at 320 milliampere per gram, so we are losing nearly 40%, nearly 60% of our discharge capacities. So however, good news is charge rate capability is so nice. So discharge rate capability is not good, but charge rate capability is so amazing. So even 1000 milliampere per gram, so this sample shows very good rate capability. Charge rate capability. So of course, electric vehicle applications. So most important character is quick charge abilities. So therefore, possibly, so this sample can be used for practical, so electric vehicle applications in the future. So okay, so last session of my talk is rock salt type electrode materials. So we have many advances for layer system. And also my final topic is rock salt type layer structures. So details about the rock salt structure is I have published one review paper here. And also so last section is mainly about this publication, Nature Materials publications. So now we synthesize rock salt electrode materials. So chemistry is vanadium ions, lithium-rich vanadium chemistry. So this sample shows very large reversible capacity, and also this sample is actually low crystallinity rock salt type materials synthesized by high energy mechanical milling. So this sample shows very high reversible capacity and also very good capacity tensions. So again, similar to manganese ions, vanadium ion, pentavalent vanadium ion is a highly soluble chemicals into electrolyte solution. Therefore, highly concentrated electrolyte solution effectively suppress dissolutions. So this is after storage test with a conventional electrolyte and also concentrated electrolyte solution at 50 degrees Celsius for 2 days. So now, so yellow coloration, clearly evidence of a manganese vanadium dissolution with conventional electrolyte solution. So, but you cannot observe any evidence of a dissolution of vanadium ions for highly concentrated electrolyte solution, leading to good reversible capacity and good capacity retentions. So, however, important point is that this sample has a very unique phase transition process. Volume change cannot be observed. Diffraction line position is always same. So we really surprised these results. Then we carefully analyzed its origin, zero volume change. So our conclusion is so this is the result of total X-ray scattering. So and also this is a diffraction data and also PDF data. So now when you see diffraction data, after charging, 202 diffraction line intensity increases, 200 is a decrease. So this is because of a vanadium ion migration to neighboring tetrahedral sites. So pentavalent vanadium ion is formed upon charging. So vanadium ion is a very small ions migrate to small tetrahedral sites. However, this is a migration process is reversible upon discharging. Vanadium ion migrate back to octahedral sites. So similar trend is observed for PDF data. So why we have a zero volume change character? So let me explain by using this graph. We check the volume change over different vanadium-based rock salt type materials based on the vanadium ions. And also lithium contents is different. So stoichiometric sample and also lithium-rich samples here. So when we observe a volume change for rock salt lithium VO2, you can observe a volume shrinkage after charging, as expected. Because the oxidation of vanadium ions results in a more shrinkage and also extraction of lithium ions, so increasing a free volume in the structure results in a shrinkage, as expected. So however, very unique materials here, lithium-rich vanadium oxide. Now, after charging, you can see volume expansions. So this is because of upon charging, vanadium ion migrate to small tetrahedral sites. As a result, electrostatic interaction is more increased, leading to expansions. So, and also expansion and shrinkage, we have two different factors. So this is influenced by lithium contents. So because this is the same with the thermal expansions. So increasing lithium contents, meaning you have a more oxygen, metallic, ionic bonding nature is increased. So when you compare the thermal expansion for more ionic compounds and covalent compounds. So for example, diamond, typical covalent materials, shows a very small thermal expansions. This is also same. So as increasing lithium contents, meaning a more ionic bonding nature is increased. Therefore, so similar to thermal expansions, so volume exchange upon charging is also increased. And also our materials found in here, so moderate amount of lithium contents. So now, so we can design zero volume change materials by optimizing chemical composition and also so vanadium ion contents. So this is important results for our materials application to solid state batteries. So solid state battery with algyl type sulfide electrodes. So typically, many people use a very high stack pressure like this, 200 megapascal. Because the conventional rare materials, we cannot avoid a volume expansion, shrinkage. So by applying a very high stack pressure, so they can make a more reversible operations. However, even applying a very high stack pressure in general with rare materials, cyclability is not good. However, our zero volume change materials, now you can see very high reverse process. And also we surprised these results, 1,000 cycles, no capacity failing. So now we can design very high long life solid state batteries with zero volume change materials. And the next step is to eliminate this stack pressure. So now this is the results over recent results without stack pressure. Of course, by applying a stack pressure, we can obtain much better results. But even without stack pressure, external pressure, so this sample shows very good cyclability. So possibly by optimizing positive and negative electrode materials with small volume change, maybe we can design practical solid state applications in the future. So this is the conclusion of my talk, and also thank you for my students and also collaborators and also research funding. Thank you for your kind attention.
And thank you very much for your talk. And now we have the last talk of the first session. And Professor Kazuhiko Matsumoto will give a talk about sodium-ion batteries.
Thank you, Mr. Chairman, for your kind introduction. I'm Kazu Matsumoto of Kyoto University. Very happy to be here. So I'm going to talk on impact of temperature on the performance of sodium secondary batteries. So as the previous speakers talked, we need energy storage systems in our daily lives. And previously, we used a lot for mobile machines, but nowadays we need large-scale batteries for electric vehicles and also power supply. And I'm going to talk about sodium secondary batteries and also the impact of temperature. First, I want to talk a little bit about lithium resources. So this slide shows lithium resources over the world. With the size of coin cell. So large coin cell means large lithium resources. And actually lithium resources are in many places all over the world, but big sources are actually unevenly distributed in the South America. So that we would expect the unstable price of lithium resources, and actually the price is increasing. And compared to this lithium resources, sodium resources are everywhere, and even in the crust and also the seawater. And so we believe that price is more stable. And the important factor of my talk, our work, is the ionic liquids, because we are working at high temperatures. So ionic liquids are composed of only ionic species and liquid at around room temperature without any solvent. And then they have unique properties including low volatility and low flammability, wide liquid phase temperature range, and high electrochemical stability. And based on these unique properties, we could use them as safe electrolytes for secondary batteries. And these are the typical ionic species for ionic liquids. And we need a bulky, large organic cations. And also, typically, we use fluorine-containing anions for ionic liquids. And in the application for that secondary batteries, we usually add metal salts. So in the case of sodium batteries, we add sodium salt to organic ionic liquids. Here, I'm showing a wide temperature operation of sodium-ion batteries with ionic liquids. So these are the typical applications at different temperatures. And we have some low temperature application and high temperature application. But today's lithium-ion batteries are usually operated between -20 up to 60 degrees C. The high temperature limit is, there are several factors, but the important thing is the stability of SEI, so the surface film on the negative electrode. So usually it breaks around this temperature, so we cannot go higher. But by using ionic liquids, we can extend the temperature range, and we typically work around 90 degrees C because sodium metal melts above that temperature. And then we call it the intermediate temperature. So we can use materials which we use around room temperature, but without using special materials. And also we can get some waste heat from industry and also even from vehicles, cars. And typically an ionic species is this FSA anion, where we have 2 fluorine on the sulfonyl amide type of structure. So ion diffusion in the electrolyte, interfacial process, and ion diffusion in the electrode, all the possible rate determining steps can be improved at intermediate temperatures. And of course, there are a lot of challenges to operate batteries at high temperatures, but still the intermediate temperature operation is very attractive. I'm showing two examples of advantages for intermediate temperature operations. And this is the appearance of the deposited sodium metal after 50 cycle alternate metal deposition dissolution. At room temperature, as we see in the case of lithium metal, the mossy, dent-like, whisker-like deposition are here. But then at 90 degrees C, so close to its melting point of sodium metal, even after 50 cycles, the surface is flat and is shiny, and we don't see dead sodium metal a lot. So this is a very good for as an application for metal batteries, and also as a counter electrode for half cell test. The other example is the rate capability of electrode materials. Here I'm showing the Na3V2 PO43 type, Nasicon type positive electrode. So this is the left-hand side is the rate capability test, where when we increase current density, the capacity usually decreases. This is a typical behavior at room temperature, but at 90 degrees C, we see the only a small drop of capacity, even at the 4,000 milliampere per gram. And of course, we expect the high, fast ion diffusion. But not only that, when we take a look at that Nyquist plot of that NVP symmetric cell, the semicircle corresponding to interfacial process decreases from 25 to 90 degrees C, very largely decreases, suggesting not only ion transport, but also interfacial electrochemical reaction is really enhanced just you go up to 90 degrees C. So based on these data, we made a sodium Nasicon full cell. So typically, when we measure the performance of positive electrode, we make half cell with excess sodium metal. But in this case, we added, put only restricted amount of sodium metal on the negative electrode. So in this case, it's a negative to positive capacity ratio equals 2. And then we did that, full cell test. And left-hand side is again 25 degrees C, and then the cell capacity decreases after 30 cycles. But at 90 degrees C, in the same condition, the capacity is kept over 120 cycles. So obviously, the sodium metal deposition actually controls the performance of this type of full cell. Here, for anode-free cell, I'm not talking about a lot, but we also did some work for this, and not showing performance because of time limitation, but just showing how to treat the surface of aluminum substrate for this purpose. So there are a lot of techniques known for the surface treatment of aluminum metal for sodium metal batteries, like carbon coating. But here we just treat it at high temperature annealing, and then we can control the orientation of aluminum, crystal preferred orientation to 100, and then fluorinated the surface with diluted hydrofluoric acid, which gives this surface morphology. And then by using this, we can really improve the performance of anode-free cell. Details is in our recent publication. So from here, I'm talking about a bit different sodium batteries with the beta alumina solid electrolyte. So sodium sulfur batteries are already commercialized by some companies in Japan. For example, NGK is a famous company. So typically, we have liquid sodium metal in the negative electrode and beta alumina solid electrolyte. And then sulfur, or actually during discharging, we see sodium polysulfide. And in order to keep this polysulfide in the liquid state, we have to operate this battery over 300 degrees C. but we have ionic liquid. So by adding thermally stable ionic liquid, actually polysulfide does not need to be liquid, and it can be solid. And then we can work, our target temperature was 150 degrees C. And after a long-term screening, we reached this inorganic ionic liquid with the sodium triflate and cesium TFSA. And this triflate ion is actually necessary to dissolve polysulfide. But anyway, we made that a flat type cell and then discharge. And this is the discharge charge curves with the different polysulfide species. And again, we use that inorganic ionic liquid and beta alumina for this purpose. And then for the first discharge, we get 800 milliampere per gram, nearly corresponding to the formation of Na2S2. And then, but this case, the current was not very high, so we increased the current and did that cycle test over 1,000 cycles. In this type of sodium sulfur battery is very unstable, and even 1,000 cycle is very, very challenging. Unfortunately, the capacity is somewhat fluctuating, but that because of the use of the capacity in this region. We are still not sure why, but in this low voltage region, sometimes we can use that capacity and sometimes we cannot. There seems to be some surface contact can affect such activity, but still we see the average capacity of 381 milliampere hour per gram, and Coulombic efficiency is nearly 100%. Then we moved to that sodium metal deposition behavior. So because we worked at low temperature and also at high temperature, we were wondering what happens at the interface and compare the solid sodium metal and liquid sodium metal on the beta alumina solid electrolyte. Because melting point is 97 degrees C, and if we work at 90 degrees C, it's solid sodium metal. And if we work at 105 degrees C, it's liquid sodium metal. And we expect the bad contact in the case of solid sodium metal and beta alumina. And how the state of sodium metal affect the battery performance. So what we did was first we worked on sodium metal symmetric cells with solid sodium and liquid sodium. So both sides solid sodium and both sides are liquid sodium in this case. And we see that the large polarization in the case of solid sodium metal compared to liquid sodium. Obviously from the bad contact between metal and beta alumina. And the big difference is that critical current density, where in the case of solid sodium metal, we see short circuit at 30 milliampere per square centimeter. But in the case of liquid sodium, it can go up to a very high current density of 130 milliampere per square centimeter. And then we moved to that half cell test with solid sodium and liquid sodium metal combined with again Nascon type Na3V2PO43 positive electrode. But here the beta alumina is solid, and then this Nascon type is of course solid. So solid-solid contact is no very good. So again, we added ionic liquid a little bit as an interface and solid ion conductor. Then we compare the two different cases, the cycle performance over like 500 cycles. So in the case of liquid sodium metal, it can go over 500 cycles, and we see 95.2% retention. It's very stable and without any problem. After this cycle test, we open the cell, but nothing happens. Well, when in the case of solid sodium, the capacity decreases just in the 100 cycles and then drops after 100 cycles. And we saw that surface of that beta alumina after the cycling test. Here, even from our visually, we can confirm the damages, And by microscopic observation, we saw a crack or even some holes. Seems to be a very harsh reaction occurs on the beta alumina with the solid sodium metal. So when we work with solid metal, we obviously have to be very careful for even if we use a solid state electrolyte. So this is a summary of my talk. And first, the intermediate temperature operation with ionic liquids enables high sodium metal deposition, dissolution efficiency, and also high rate performance of the positive electrode. In the second, long-term charge discharge was achieved with the sodium sulfur cell containing inorganic ionic liquid in the positive electrode room. And then the third one is liquid sodium metal provides a more stable charge discharge behavior than the solid sodium metal, owing to the high interfacial compatibility. Thank you for your kind attention.
Okay, now I think the break was enough, and now we would like to sorry, I didn't mean you. We would like to move on to the next session, and in the second session we have 3 speakers, and sorry. The first speaker of the second session is Professor Egbert Fiegemeyer, and please welcome.
Thank you very much, and thank you very much for inviting me here. It's a great pleasure and a great honor also to come back here after many years. My first time here was actually trying to sell carbon nanotubes to Korean cell manufacturers in 2010, so a long time. And this is also a little bit my background. It explains a little bit the topic, is that I worked a lot in industry with new materials, innovative materials, and also facing the challenges. And then asking myself, okay, how do we get innovation into the market, and what does this all mean? This is part also of my lecture where I try to meld a little bit technology and also a little innovation management, and a few thoughts we may want to discuss. The more scientific part will come tomorrow, deep dive then into pre-lithiation and also interfaces, but today is, let's say, the light introduction. So just shortly an introduction, we have great new infrastructure work. Maybe Professor Martin Winter is well known to the community. Professor De Couvazot is a colleague of mine. We just enabled this research facility focusing on lifetime and reliability of batteries. And if you're around in Europe, please contact me. You're very welcome to visit us. I would be very happy to invite people. The motivation we have heard before, I always found that a bit impressive. How long we know that we have to do something and we don't do. And it's really urging. Already in the late 19th century, it was known that CO2 is warming, let's say, has a warming effect. In the 70s, the big oil companies knew it. And in my old childhood room, I found this old journal where there was a long article in '89 about, okay, climate change is actually happening. So this is really, let's say, a background of a lot of motivation. And a lot of motivation ended up then in the European Green Deal. I give it, sorry for this, let's say, European-German perspective of it. And I'm very curious also to reflect it with you, how, let's say, the Asian viewpoint on this is. The Commission filed, let's say, a ban of new combustion engines by 2035, which is currently under debate again. But this is current law, and it's part of, let's say, the Green Deal and following the Paris Agreement. So this is a strong push by the Commission, a strong push towards, let's say, electrification of traffic, however that will happen. I like to show this slide, not because I like history too much, but one thing we can learn out of this. You see all, and if you are from the battery field, you know all these milestones in the battery development, and what you see is the time frames. And interesting, it takes decades to develop a new technology, new battery technology, and that's often underestimated. Also, when we talk about research periods which we need to consider, you need really a lot of patience. Also, the last thing, I mean, the lithium-ion battery was many decades, and this was also now with the next generation. Solid-state technologies will take their time, despite all the hooray about this is now the new battery revolution. I don't know how many times we have heard that a new battery revolution is just on the edge. So this is really, let's say, giving us a little lesson learned, because it's a complex system. So that's one of the take-home messages. Same for lithium-ion battery. This was a really big thing, but it took also decades to come to the systems as we have them now. And over the last 20 years, another, let's say, new generations of lithium-ion batteries have developed. This has been at the forefront. There was these three, but many others. There's also, I think the list is not complete, especially also from the Japanese forefront of research and industry research. Let's say at Sony, they were very important figures who pushed it into, let's say, commercialization. So this is another thing, and we move from lithium metal to lithium ion. Maybe we move back to lithium metal. We see how this goes. As we have seen before, this whole thing is, let's say, shuffling lithium ion around. It's actually, despite being a chemist myself, the good thing is about not doing chemistry here. It's basically intercalating lithium in between the different potentials and stabilizing the electrolyte at 4+ volt at a very negative potential with a stable interface. So that's really the breakthrough. This is current technology. This is state of the art. And I think at the most I don't need to explain it to this. This is also something which is well known in the community, of course, the different technologies. And why do I show this? Because things change over time. And I will show this in the end, that the perspective on our technologies seem to change dramatically at the moment. I mean, a couple of years ago, everybody would have said NMC gives you the best compromise, and basically everything. Safety is sort of an issue we should still address. We know that they can catch fire. But all the others seem to be right on, let's say, on track, even though maybe cost also is still an issue with NMC. Lithium iron phosphate, interesting, has been, it's by many countries actually abandoned. I will come back to this issue, even though it has a quite good, let's say, compromise of properties. Specific energy density is not quite good, and since everybody was racing for range in electrification, this was, of course, then often a killer criterion for this. Sodium ion, I don't know about safety so much, very little experience. I haven't seen too many experiments. They're just rumors in the field. Energy density may be comparable to lithium iron phosphate. Very attractive, of course, when the lithium price is high. When the lithium price is low, things drop also. The attention towards towards sodium ion goes down. So the market is a very volatile thing, and the attention span is very volatile. And this is what we as researchers also struggle with, because industry goes back and forth, and the politicians go back and forth on this. Solid state promise we have, and we have heard this morning, this afternoon. Sorry, I'm still in the jet lag. It's somewhere around 9 at home, and coming straight from the plane. But we have heard this afternoon a lot about lithium solid state, and it has undoubtedly a promise. I think is a lot of work to be done, and a very complex system, super science I find, super scientific, interesting. And this is just the time it takes to bring it, let's say, to an application. So why do I show also a lot of old graphs? Because it's all worthwhile revisiting. This, for example, the graph watt versus kg and watt hours versus kg, which I find always revealing where you place things. And we see NMC, of course, and all compared to all the other battery technologies. I will come back to this. Because What we have seen, and me as a researcher, I go very deep into silicon. This is really our stronghold there. I come also from a company who produces silicon alloys, where silicon and NMC 811 or even less cobalt is the way to go. And you need, let's say, this was, or it is the obvious roadmap towards very high energy density and specific energies. So I think every large OEM has this on the track or on their roadmap. Let's say the 400 watt-hours per kg with a high silicon content. But you need a lot of also enabling technologies for this. We have seen the interface stabilization of silicon is a tough one. And 20, 30 years of research have not really solved this problem. There are some cells on the market with low silicon, but they still have issues because of the expansion issue. The alloying is there, let's say the volume expansion in particular, breaking the SEI, is compromising safety and lifetime. So we're working on this. We work a lot on pre-lithiation to make things work to compensate the reversible losses. So back to that graph, and this is why I picked this topic also for today, because over the last 2 years things have happened, which have in Europe at least gone more or less unnoticed in the community, that LFP suddenly is back in the race. We see in China massive increase of LFP. China always promoted LFP, and the rest of the world somehow said, LFP, who is LFP? Chinese buses maybe. No, I think it's really has picked up speed, and I will show you why also in a moment. So this is back in the race. The return of the Jedi is the return of the LFP. For several reasons, for good reasons. And one is, or the driver in our community is, and that's why I also asked, what do we need for better batteries? The complete price decline. I walked around still last year, talking about 100 euro per kilowatt hour, and that gave a certain frame. Let's say, okay, this will foster electrification, this is quite linear, But the rumors, and this is from various sources confirmed, we are at $50 even per kilowatt hour, and on stack level on $60, $70 per kilowatt hour. And that changes the story massively because it enables a lot of new applications, and it really has implications on all the roadmaps of all automotive companies. And of course, this is LFP technology down here. And that, of course, if that's half the price of NMC, you may think you make compromises on the on range or energy density in return. So, and at the same time, battery margins are being squeezed. This is also what we see at the moment. Really, China pushes so hard. They take people I know working in the field in China down to 3%, basically making losses on this. Nevertheless, this is reality. And we have to face it, that this is at levels nobody would have expected. And this is where it becomes really interesting, because it's happening over and over. We saw it in the photovoltaics market. We saw it in the LED market. We saw it in the digital photography market. It goes always faster than what you foresee. People think linear, but happening is logarithmic. So that's really a game changer, I would call it, which is really rather new. So consequent ones, electrification of traffic. We have done great progress, and I think sometimes it's a clapping of shoulders. We have improved, let's say, in the last 10 years from a really moderate range up to a very significant range where practical cars are working for a reasonable price, with good lifetime, with even also a very good CO2 balance sheet by now, which was a big, major issue to discuss in Europe also. So that actually going down the cobalt road, everything, I think, well, already better than most people expected, something linear and a very good quality. The vehicle prices at the moment, and this is the implication I was talking about this dropping prices into, let's say, unknown territory, is that the electric vehicles are cheaper than the combustion engine driven cars. We talk about China at the moment. nevertheless, we will see, I mean, we know from other technologies, this will move over to other countries very quickly because they don't stop at the border and say, oh, this is only for our country. So the question is, will they be successful on the, let's say, Japanese market or Korean market or the European market, on the US market? We'll see what happens. But it becomes a competition, serious competition. And it was sort of kind of in the pipeline, but nobody really wanted to admit to it, let's say. So this is really where it behaves. We see in Europe battery electric vehicles going up. This is not the latest graph. It actually has sort of flattened out. This is sort of a bit of a cheat of myself. It has not gone up anymore. And that has brought up the issue, oh, do we need electric at all? So everything questioned again, everything all over. But I think it's just a bump, let's say, in the interest. And we see what happens when the battery electric vehicle cars are actually cheaper than combustion cars, with lower maintenance, by the way. Here, this is, I think, what made really the headlines. 50% of cars in China are full electric or plug-in hybrid, but the plug-in hybrid part is, I think, 10% of the electric part, so it's there, but it's not a major player. And if you think, for example, Volkswagen has really the issue that China was their biggest single market, but only for combustion. They have next to zero share in battery electric vehicles. For them, it's dramatic because they lose, let's say, this market goes down very rapidly, and they're only in this market successful. So this is really a very, let's say, critical moment for the companies, and we see it in Europe that this has rung a lot of alarm bells at the moment. So this changes, let's say, I would say the battery electric world. A few worldwide figures which I can skip rather quickly. It's a forecast. This is an older forecast also. I think the different markets, China, Europe, US, it's a bit difficult to read, I must admit. Sorry about that. And here, this is what I discuss also about with students a lot. And I find this I always try to understand when innovation makes it to the market, when it is successful, and how it happens. And they are good. The economics people have some good ideas about this and a lot of examples about this. Very often you see such an S-curve. Let's say a long time nothing happens. We've seen that in lithium-ion battery. Then a lot happens in a short period of time, sort of the gold rush period. A lot of improvement, like in the combustion engine. We saw major improvements in the 80s and 90s with the diesel injection pump. And suddenly we came to a level where actually improvement was very expensive. The last years, improvement on the combustion engine is super expensive. So many engineers have to work for that last digit of percentage of efficiency, and so that it's almost not measurable anymore. And if at the same time you have this other curve from the, let's say, battery electric vehicles, for example, and then they match at some point. And I think we are pretty much here. And then things go very rapidly. And to bring this further, because I thought, well, a battery technology is one challenge, but the automotive companies actually have another challenge. They have the digitalization, autonomous driving, let's say the smartphone on four wheels, sometimes on two wheels also, which comes in at the same time. So this is really a very toxic situation for the established players. And we have seen this in the phone and photography field. The analog photography first was hit by digital photography generally with the cameras, and then the mobile phones came, and that was really the death. So this is, and you see that in quite a few technologies, that this is a two-level shaved system, which really brings trouble to the established manufacturers here. It can go very fast. This I like also to show. See, so where is the car here, and where is the horse there? This went very quickly. After people also said, I want faster horses and not a stinky car. So everybody always says in Germany, I don't know how it is in Korea, but is this huge discussion, we don't want electric, we don't need electric, electric sucks. That's still more than 50% of the people, and I would say 80% of the politicians. What do you think about? It's very popular to say so. Anyway, consequence two, I don't know how with the time, I think I need to accelerate a bit because the fast dropping costs and prices of batteries have also implications on grid storage. Grid storage is the second big application which currently picks up speed. No question why you need it. Fluctuating renewable energies, solar, wind, need some storage to back up the system. We see a tremendous, as a photovoltaics, I would call it a revolution. It goes really skyrocketing. Last year we had something like 500 gigawatt peak worldwide increase. So that picks up speed. So storage needs to come along somehow. And you see we have made a few studies. I think that's more or less for most industrialized countries, I would say, valid. The battery storage total dominated by lithium-ion here, which goes really up more than linear, definitely. That's one thing. This is households mainly. People's having their storage down in their cellar, or I would put it in the garage outside, not in the cellar. I like my house. And the other technologies almost don't play a role. What's new also, that's really developed, I would say, post-corona development, all of this, is the large grid storage. Where also, if you would have asked people 5-10 years ago, if gigawatt-hour systems are feasible, they would have said, are you crazy? Who wants to pay for this? And they don't last, and they are too expensive, and they are too expensive. But with these low costs, you see suddenly projects popping up, which really also brings us into this very steep slope of installed grid-connected battery storage systems, which is new. There's a business case for it suddenly, which had not been really anticipated on this size. It was always talking about 5 megawatt hour, 10 megawatt hour. Now we're talking about 500 and a gigawatt hour. So that's an implication, of course, of the low prices, which then is, and here also another, let's say, a story long enough to, lead acid was a stationary storage technology of the choice for a very long time. And I talked to lead acid producers who believed in 2014 still nobody wants lithium-ion. It's too expensive and maybe not safe or whatever. They found a reason. And you see, this is the disruption of this technology, how fast this goes. And this was in 2 years from where lithium-ion took basically over the market. Now it's next to 100%. So this can go very quickly, one technology out and the other one in. So, coming to conclusions, do we need better batteries? And if you're going to go through all these efforts, safety, yes, we need to keep working on this. Excellence happens. Energy density, sufficient, I would say, for electric mobility, but it's a subjective criteria. Innovation, materials and processing, scrap rate is a big thing where we need to be much better. And also China needs to become better there. It's a waste of material, and also it's a cost matter. What do we have? Lifetime, the longer the better. We're pretty good in this. Power density, combined lifetime and fast charging. That's the big thing. Everybody who drives electric avoids to go fast charging because knowing you're working on your lifetime. I had a friend where Tesla said, no, you cannot use your car anymore because you're always using fast charge. You're killing our battery. They shut him down the car for using the fast chargers. General, invent a battery which does not need a complex battery pack architecture. That would be a winner. No thermal management. And is fully safe at almost all conditions. So the perfect battery, that's what we need. Disrupt the battery market with that. Because on the stack level and on the system level, this is quite a cost driver still, where better batteries in that respect could help a lot. Yes, but my take-home message is current batteries enable market breakthroughs in automotive and stationary right now. And other application, aviation found it very interesting, robotic. I mean, we need a lot of better batteries, but application specific, not generally the better battery. There's a slogan also, better battery, build better batteries, but it's always application if you like, I think that my time is up, but you can read all these expert opinions meeting reality, like lithium iron phosphate is out of business, car with less than 5 cannot be sold, cylindrical cells are too expensive to assemble, therefore hard case will always the winner. By now, all the OEMs working back on cylindrical cells. Trucks can only run on hydrogen, that's a good one. Battery electric trucks entering the market on large scale. This is happening. This also, I didn't have time to talk about that. Batteries cannot serve high voltage grid because they're too expensive. But I've shown the opposite. Cost of batteries can never go below 300 euro per kilowatt hour. I don't know how it was discussed in Japan, for example, in the early days when you made price projections. What would you have said 10 years ago? Coming from the electronics industry, of course. So that's, and then I thank very much for the nice Hyundai I drive myself, for the Korean car. Very nice car, actually. I thank Sang for the for organizing this. This is a great initiative, and for the collaboration. Thank you for your attention. Thank you.
And thank you very much for your general overview about the battery technology and the market. And the next speaker is Dr. Moritz Hantel, and he's talking about the refining carbon for next generation batteries.
Thanks a lot, and first of all, thank you to Kost for the organizers of the team, Juhan, Sang, to make this event happen, and for giving me the opportunity to be today here and give this presentation. And I think I have a very good follow-up on the presentation we just had. Now looking a little bit more on the resource side, going a little bit, as you can see, it's now going in the direction of graphite, of carbon, and also this plays an important role. So it's about redefining carbon for next generation batteries, but next generation batteries doesn't mean technology necessarily next generation, but also next generation what we get on the road. We have just seen prices are declining and we need to compete, and the growth is continuing. So in the end, to summarize almost the presentation from before, we have a huge increase at the moment in renewable energies. And I looked in the same report from the IEA, and what they said, they assume till 2030 we have an increase of 5,500 gigawatts, so 5.5 terawatt of renewable energy coming to the grid, which will allow about 50% of the global energy production being renewable. With this comes a huge challenge, because it's a fluctuating source, and to make this useful we need energy storage. And also from an energy storage perspective, in this case, it's not about how much energy we store, but more what's the power, the regulating power, which needs to be in the grid to allow a combination of renewable energy and to sustain the power requirements which are at the moment in the grid. And based on the IRA report, they assume that around 1.5 terawatt of power, grid power, needs to be installed with batteries, with energy storage, to get these renewable energy storage systems going. And then last but not least, and I think that's what we also have, we have a decarbonization in the mobility sector. xEVs are growing, and what I found very interesting is we are always still looking into the battery market in terms of how many gigawatt hours, terawatt hours we add on top. An interesting point here is, and what I found in the report is, they expect that we add annually around the 40 million xEVs by 2030, meaning the production grows from, at the moment, around 13 to 14 million cars, xEVs, so hybrids, plug-in hybrids and battery electric vehicles, to 41 million in total in 2030. And that, I think it's a very nice thing. It's like, at the moment, we are working together to enable, in this regard, a greener tomorrow. So I'm also a happy owner of EVs in my family. So 2 examples, we drive, we had one of the first Kia EV6 in Germany. So we're driving it by almost 3 years now. And we have an BMW, an i4. And 2 examples here to show that EVs are really in the market and they have reached the mainstream majority. So in summer we were driving, I'm living close to Frankfurt, so we're driving all over Europe, through France to Spain, and it's like a nice name in this regard. Finisterre means it's like the end of Earth. So it's a nice coastal town in Spain. It's like, so we're driving from the center of Europe, Frankfurt area, to the end of Earth in Europe. And the round trip was 15 days. We drove more than 5,000 kilometers. We had over the tour, and that's I think a feature which is often forgotten, we recuperated 190 kilowatt hours. So just instead of wasting our braking energy, we recuperated it. We charged almost 1 megawatt hour, so 919 kilowatt hours charged in total. And now with this system, the median charged energy was around 30 kilowatt hours, and it took us 24 minutes, which is okay for a holiday, but maybe for a day-to-day trip, a little bit too long. So looking now in the EV6, which has the advantage of an 800 volt system, we're going now into fast charging. And then this around 30 kilowatt hours are also possible in 7 minutes. Still, I think to get the adoption rate even higher, charging is still one of the topics which needs to be adapted. And one way to do this is, as we just also heard before, improving batteries. So let's look a little bit from the resource side now. So looking, in this case, taking an example, the Chevy Volt, which was, I think, the third best-selling EV in the US last year. So it's not a Tesla, but like just more a general car. We have here 288 individual lithium-ion battery cells inside, 350 volt system, 65 kilowatt hours, and assuming an NMC 811 mix, we have quite a mix of minerals which are in the car. But the interesting part is what we always forget is we are all looking from a scientific perspective more in this mix, in the cathode chemistry, in the anode chemistry, in the electrolyte, but how much is it really in a car? So looking here is like breaking it a little bit down per kilowatt hour, and also in this example, we're talking substantial numbers of minerals which need to go in one car. And these minerals needs to be mined, refined, processed, optimized at a price tag that we can achieve this, what we just heard, $50 per kilowatt hour, for example, with an LFP chemistry. Very often, and that's also a little bit the focus of today, is the carbon part, which is neglected, because typically we're looking into the nickel, we're looking into the cobalt, looking into the lithium, which are substantial, but rarely anyone is talking about the carbon. And summing it up, in this case, we have 61 kilograms of carbon in this car, which is in sum the biggest amount of any mineral in the system. So how does this further develop in the next years with our projections? So taking here a more conservative market report, looking into the next years, the estimation up to 2030, we see that the global battery market is around growing to 4 terawatt hours. Depending on which crystal ball you read, it might be more, it might be a little bit less, but I think it's a good number. Looking now from a carbon perspective, so AAM, anode active material, so carbon, even though we talk about silicon anodes, typically a silicon anode is 5 to 10% silicon and the rest is still graphite. So graphite is still the dominating factor in the anode side. And what we measure here is now the amount of anode active material required to power this kind of batteries. And we're talking now thousands of 1,000 tons. So KT, kilotons, and we're talking here in the end of the decade around 3,000 kilotons of refined anode active material which is required to power this kind of batteries. Looking now into graphite, and that's I think also an interesting topic, is we have two kind of graphites in the market. We have the synthetic graphite, where you produce a synthetic graphite directly into an anode active material, where you have a conversion ratio 1:1. And then there's the natural graphite, where you mine flake graphite, and then you convert it, you process it to anode active material, and in this case the conversion factor is 2:1, meaning looking into the demand of graphite, we are talking around 4,000 kilotons of graphite, which needs to be either synthetically produced or mined by the end of the decade. So the question is, can the supply chain keep up with this? And what we have seen the last years is, and I have here some examples, is for sure we have global supply chains, we have issues of interruptions. So I think we had a nice example a few years ago with the Ever Given being stuck in the Suez Channel. And it was just one container vessel, but the outcry was more that another 300 vessels were stuck. And it caused delays of weeks in the supply chain. Another topic at the moment we're facing is trade barriers coming back up. So in this case, for sure, focusing on the graphite, but we saw it from Europe, who tried to get a little bit out of the Chinese reliance. On the other side, China imposing trade restrictions on graphite in terms of, at the moment, if you want to export, you need to register. At the moment, they export, but we never know. And then on the other side, with the US imposing tariffs for Chinese graphite, making it a more volatile market system. And then for sure we have the market dominance of China. That's the reason why China is also mentioned so many times in the news. In 2023, about 70% graphite was mined in China. 99% of the spherical graphite, which is a precursor for natural AAM, was coming out of China. 80% of the anode active material from a natural graphite basis was coming out of China. And we have also on the synthetic side 70 and 97%. So in the end, without China at the moment, there is no anode. Without anode, there is no battery. And that's just where we come into play. So diversification of the supply chain is important. And with this, I would like to introduce who is Northern Graphite. So Northern Graphite, in short, NGC, is a mining and battery materials company. The headquarters is in Canada. Overall, we are about 100 employees, 5 sites, 3 continents, and the expertise is on mining, in-house battery testing, and battery materials. And you can see our footprint in terms of offices is more in Canada. That's where also the headquarters is. We have assets in Namibia and in Europe. Looking there a little bit into the details, what NGC battery materials can offer is on the one side we have carbon expertise, developing carbons, and I will show there some examples later, but also having the expertise to vertically integrate from a source to the final product, especially a product in the battery space, and then also having the capabilities of lab testing and battery testing capabilities, where it's important to also see that the materials perform under rather real conditions. Looking at our assets a little bit and going here from the left to the right. So in Canada we have 2 mines, and with Lac des Îles, which I want to mention, we have the only operational graphite mine in North America. So in the whole of North America, this is the only mine producing natural flake graphite, and this already for 30 years. What we're planning at the moment is like a processing plant for anode active material, also in Canada, which will be in Baie-Comeau with a deep water harbor access. And then we have another mining asset in Namibia. And then we have, with the battery materials group, we have an office and lab space in Germany, close to Frankfurt. And we have a production of our hard carbon additive, which I will introduce a little bit later, in Rotterdam. Quick dive, how is mining of graphite working? And I hope the video is starting. So what we have here is, and you see on the satellite image, this is the mine in LDI, and this is an open pit mine. So in the end, what we're doing is, and I hope this works, yes it works. So in the end, it's an open pit mine, just with blasting, the ore is produced, the ore is then processed, and then with around 6 to 10% of graphite in the ore, we produce natural flaked graphite. So this processing is happening in a processing plant, and then these little black pillars you see here around is like always one big bag, 1 ton of natural graphite. That's the intermediate stock from processing before it goes out to the customers. And at the moment, since the demand is rising, we are ramping up from 15,000 tons per year to 25,000 tons per year. But you have seen the numbers before. We're talking thousands of tons required. A little look at Baie-Comeau, and just like in a bigger one advantage, and that's the reason why Canada, processing requires energy. And one big advantage of Canada is the hydropower in the area, meaning we can run the processing 100% with renewable energies, meaning in the end it's a rather CO2 neutral or low CO2 material compared to, for example, synthetic graphite, which is typically even requiring a lot of energy and also byproducts from steel or petroleum industry. And then the last part, what we have in Europe, in the port of Rotterdam, where we have our demonstrator plant for porocarb, a synthetic carbon additive, where we produce, and that's like the additive side, 100 tons per year at the moment, and at the moment we use this as a template to further ramp up the system. So what do we do actually? So the first thing what we're doing is BAM, what we call it, battery anode material, to be a little bit diverse from the anode active material. And in the end, it's a natural graphite-based system, meaning we have, and we're working on the fully integration, starting on the left with the mining, going milling and shaping, purification, coating, and testing before it goes to the customers. From a product perspective, this means we have the flakes, which also go in other industrial markets. We have an intermediate product, spherical purified graphite, SPG, and we have the final coated spherical purified graphite, which is the active material used in the battery. Just a little summary from this regard, natural graphite flakes come in different sizes, purities. They're still very important for industry applications, like refractories, foundries, friction products. So in other words, also a lot of our modern technology requires in the processing graphite. But what we are now interested in is like more going into the vertical integration and enable to get natural graphite-based battery products into the market, which are out of China, to diversify the market and supply chain. So we have the SPG, where we can tailor to the needs of the customers in terms of tap density and size. And then for sure the BAM in the end, where we can, beside tailoring the 50 and tap density, also the coating which is applied defines the quality later in the material. To give there a little bit of a perspective, so typically the graphite can be then used on the anode side, and in reality it's never a pure natural graphite-based material. So typically a blend is used where still around 50–60% is coming from synthetic graphite and another 30 to 50 from the natural side to reduce, and that's I think the advantages of natural graphite, the CO2 footprint. So also bringing the footprint, the CO2 footprint of the battery down. We have the advantage of a higher specific capacitance, which for natural graphite is around 360 milliamp hours per gram. Synthetic graphite ranges to 340, 350, so it's slightly lower. Disadvantages is typically higher swelling and slightly reduced cycle life. And that's one thing what I can mention at the moment. We're working here together with Rain Carbon. The JDA was announced last week officially, where we are working especially on the coating side, where we have seen tuning the coating can mitigate issues from swelling and cycle life, and getting a natural graphite-based material very close to a synthetic graphite one. The other material we have is porocarb, which is a hard carbon, a synthetic hard carbon platform, which typically is applied as an additive in lithium-ion batteries. So how does the wording and the naming come? So it comes from open porosity and carbon backbone, porocarb, meaning we have a carbon system which is completely porous, where we have a macroporous structure network. And you can see here on the right side an example with a FIP cut, where you see the open inner porosity in the particle. And this enables in the application pathway for electrolyte, local electrolyte reservoir, and therefore enhances, beside of electric conductivity, especially the ionic conductivity. So let's have a look how this looks in reality, because one special thing is it's a single particle. So the material is not coming as an agglomerate, but the material comes as single particles, and in this case, the example, we have a particle of around 2 micrometer. If we now apply focused ion beam, we can cut this particle open, and what you then reveal is the inner morphology, the inner structure of the material, where we have open pores, and because it's a synthetic system, we can tune this pore network and also the size of the pores to a certain degree required for the application. And then just continuing to cut further through the particle to see that the pores really go through the whole system, and in the end we just went through the whole particle. So how is it used in the application? We have 3 application ranges for the material. We have, starting from the left, the all-solid-state battery, where porocarb can be applied as a protective layer, as a carbon protective layer on the anode side. Especially interesting for this anode-free design of solid-state batteries. We have a prospect as active material, since we have a porous carbon structure, which can aid as a carbon host. Projects we have in this direction is with partners, for example, in a silicon carbon, or in this case, silicon porocarb active material direction. And then for sure also the classic additive for lip, and I can also add here zip, because in the end it's for liquid electrolytes, where porocarb, due to the porosity, to the porous structure, aids as a performance additive because it enhances the ion battery and not necessarily the carbon, because the focus here is really porosity, enhancing the porosity and the ionic conductivity. So just 2 examples to show how it can be used, different advantages depending where you apply porocarb. Now looking more in a classic system, you can apply porocarb in a carbon mix either on the cathode side or the anode side or both. In the end, it's always important to have it in a carbon mix, meaning you have a classical carbon conductive additive like an acetylene black, carbon black, CNT, and you add porocarb to the mix to enhance the ionic component. And looking into the advantages you get out of the system is we see a better rate capability in terms of power. So going to higher C rates, so higher discharging powers, we see that we can recover more of the stored energy. At the same time, it improves the cycle life performance, since especially having a better, more homogeneous electrolyte reservoir and electrolyte availability helps over the lifetime of the system. Looking on the anode side, there it links more as a structural element, since porocarb is very stable, it's a very mechanical stable system, so it can help to mitigate the pressures coming up in the anode system with the swelling and charging, discharging. In addition, it provides a local ion reservoir and also there helps with the performance of especially the charging. The last part, and very similar to what we saw in the first presentation today, looking in the all-solid-state battery part, you can also apply porocarb on both the cathode and the anode side. So in this case, you have in green the porocarb on the cathode side, here in green in the anode side. And here the difference is it's not about a liquid electrolyte. Here the porosity on the cathode side is not the main factor. It's more about you add a structural element, and what we see in customer projects, adding porocarb to the cathode, they are able to better densify their systems. They avoid crack building already in the production process, which on the contrary also helps to form less cracks in the active material and has a better utilization of the active material. On the other side, looking on the anode side, especially in this anode-free design, typically a carbon protective layer is applied between the solid electrolyte and the current collector. And here the unique properties of porocarb with its porosity and also microporosity helps with the lithium diffusion. So what we see with customers is that applying porocarb instead of a classical carbon additive, they enhance this lithium deposition in the charging process and decrease their first cycle losses and overall enhance their performance both in discharge but also in cycle performance direction. So to summarize, and more details coming in the next talk on Thursday, innovation on the carbon side is still very important, since it's the biggest component still in the battery, and we need it both for the active material. We need to have a affordable active material to power our batteries, but also we should not forget the carbon additives, because also this component has still big way forward to improve the performance of the batteries. Thank you.
Yeah, thank you very much for the very interesting talk. And now we have the last presentation of today, and the next presenter will be given by Dr. Peter Axmann.
Thank you very much for your kind introduction, and thank you to the organizers for giving me the opportunity to talk here. So thanks a lot. It's an honor for me to be here for several times again in South Korea. And I will talk about what you need if you go from the lab to the larger scale of a material, so from the material to the real lithium-ion cell. ZSW is a non-profit organization. We have 350 co-workers overall working on all regions of renewable energy. And the battery part is done with more than 150 people here in different areas. So we saw this several times. Lithium-ion cells have become an integral part of life, and we see that the consumer electronics segment, the grid energy and industry segment, and the transportation sector, and we have, let's say, growing markets in the last two mentioned sectors. We have niche applications, we have future markets like robotics, like air taxis for wearable electronics. And what is the most motivating part is that batteries are more or less the key enabler for low carbon economy, and they contribute to a sustainable future. So the basic principle of lithium-ion chemistry, lithium-ion batteries, has been commercialized by Sony in 1991. They used lithium cobalt dioxide as a positive electrode material, graphite as the negative. This cell had a nominal voltage of 3.6 volt. And so these materials are more or less a prime example for host-guest chemistry applied in technology. So the working principle is shown already here. We see on the left-hand side, on the left-hand side, the negative electrode, where the electrons come during operation from the lithiated graphite, go through the outer current circle to the positive electrode and are reduced there at the cobalt oxide. So lithium moves to the internal part of the cell to maintain charge neutrality at the samples. And a real electrode stack, if we cut it and look with a cross-sectional view with SEM on this material, we see here on the left-hand side the anode, on the right-hand side the cathode, separated electronically by the separator. And these electrodes are a complex 3D arrangement with a porous structure to allow electrolyte access for the lithium transport, and a percolating conductive network for the electron transport to the current collector. So these electrodes are long tapes, and they are coiled up to form cylindrical cells, or they are stacked as prismatic cells or pouch cells. So, and how densely they're packed in a lithium-ion cell is shown here. So it's really very thin electrodes you have. They have a thickness of human hair. And so there's a lot of technology in these electrodes, and to maintain this or to reach this technology, you have to look at the material. So we saw this already again, we see it again. So the market for lithium-ion batteries, the demand is growing rapidly to 4.7 terawatt hours within the next 3 years. And so if we look at the cathode material, so at the cost of a cell, this is really dominated by the cathode material. Yes, 51% relate to the cathode materials, 24% to the manufacturing cost. about 12% to the anode, 7.3% to separator, electrode, and housings. And the costs come just because the raw materials are so expensive. They are critical raw materials with respect to availability and economical importance, and the amount is really really large. And the cost, as we saw already before, is difficult to calculate because the price is really volatile. It changed by the factor of 10 for the lithium during the last 4 years and went back to the original value, cobalt by the factor of 3. So, but the cathode material is a part where we can save a lot of energy, and you can do it on a material level. You can change the cathode material, reduce the expensive materials, replace them by more cheap materials, and on the anode side, we learned it as well before. You replace graphite by silicon, you can go to lithium or even zero excess anode materials, zero excess anodes. The driver here is to go to highest energy, to increase life, to increase safety, and to reduce cost. And on the roadmap for these high energy cathode materials, I now exclude the olivines, are the layered cathode materials, the NMC, the nickel, cobalt, manganese materials, and to increase energy. The principle is just to extend the capacity by shifting the composition to a higher nickel content. So the challenge is here that the nickel 4 oxygen bond is unstable and leads to aging. Second part is the spinel, the normal nickel manganese lithium manganese spinel. Here you just can exchange the redox pair and extend or increase the working potential from 4 to 4.7 volt and increase by that directly the energy of a cell. Problem here is that the electrolyte stability window is not enough for that. So, and we go to a third part, and these are the lithium manganese rich layered oxides, and here you extend the redox chemistry going from the transition metals and access as well oxygen redox process. And here as well structure and electrolyte stability window are the challenge which we have to face. The latter two materials are on the near future part of the roadmap, and they are really interesting because they have low nickel contents and they can be made without any cobalt, thus reducing the price drastically. So what I want to come now is material is often described just by its composition. There are material codes which relate to the elements you use, like NMC, nickel, manganese, cobalt, and the stoichiometry you use, like 811, which means 80% nickel, 1%, 10% of manganese, and 10% of cobalt, and so on. We have the LMNO, which is a high voltage spinel containing lithium, nickel, and manganese oxide. You have the LFP, the olivine structure, and LMFP. And these have different structures, they have different redox systems, different electrochemistry, and different aging phenomena. And I would just like to face here the LMNO. If we look in literature, we see that these materials, the literature data, show a broad range of different capacity ranges. Yeah? These data haven't been taken from a recent review and show data from different publications. We can say even for one material code, you have a broad range which is reported for the capacities. So there is not one fixed value you have here. And why is it so? Of course, you make the materials with different synthesis routes, sol gel, solvothermal, solid state routes. You have a different morphology. Yeah? Monolithic materials are described. Spherical polycrystalline materials. You have polyhedra, you have nanowires. And the electrochemical tests as well are different. They are cycled at different temperatures, C rate, electrode composition, loading, electrodes. And what I would focus on is the morphology, because this is really important for this difference in behavior. So, and the morphology is more or less the grain architecture you have here. Yeah? And functional materials are a very complex system with regard to that. You have here the base chemistry. On the left-hand side is given, or the base function is given by the chemistry and the real structure. Here you can learn how much milliamp hours you get out, which is the potential you run this system. But all all the real structure has 3 dimensions. Yeah? You have a crystallite side, which might be larger, which may be smaller, and this has an influence on the kinetics, on the stability of the materials. And these crystallites are then arranged in 3-dimensional structures like particles, and this particle architecture as well has an influence on kinetic and stability. And finally, these particles have a certain shape, they have a certain size distribution, and this has an influence on the processing behavior, which you finally need for going to larger cells. So we need to go to higher energy, so this is the driver, and materials are driven to the limits of stability, and this has an influence on the aging behavior on all designs of the level, and which means we have as well to go to new mitigation concepts on all levels for these type of materials. Very important even for one type of material. So what is needed if you make these materials? You need to characterize them. You need to learn how is the electrochemical behavior and what is application relevant here. So and to do so, there exist different types of cell you can use. On the left-hand side, the coin cell, which is used in the small labs, or the single-layer pouch cell, as well used in labs. You have as well multi-layer stacked cells or prismatic cells, like on the right-hand side. And from the coin cells, the lab information you can get is just the basic function of the material. So what is the powder able to deliver in terms of charge per gram? What looks the voltage profile like? What is the cycle stability on this level? But if you go to more application-relevant data, you need the milliamp hour per area or the milliamp hour per volume you can store. You need to learn about the compatibility of the positive and negative electrode. So the focus here is more or less on the electrode and on the full cell. And finally, if you go to the larger cells, you can classify your material into the industrial standard, which means energy per kilogram, energy per volume, or even cost per kilowatt hours. And here you come to the cell and cell-related processes. So the material amount you need for these cells is very low for the left-hand side, 90 milligrams for a coin cell, 400 milligrams for a single-layer pouch cell, even 160 grams for 30 amp-hour cells. This doesn't sound much, you can do it in a lab. But the problem is you cannot make such a battery in a lab because you have here a technical process leap because you need to go to double-side coated electrodes. So even for a 4.6 gram cell, you need a lot of material to go there. And the reason is you need a homogeneous, flawless coating. You need highly reproducible loadings and density of both sides coatings on the metal foil. And this you need extended over several hundreds of meter electrode length. You can see here how large the machines can look like, which you need to make such type of cells. In addition, to get this high homogeneity of the electrodes, you need homogeneous slurries. You need large amounts of that. And this has requirements to the material itself. So the material itself needs to be homogeneous. It needs to be processable. It needs to have a certain flow and mixing behavior, and you need to have it in large amounts to go to these machines. Yeah, and large amounts mean our small coating lines at ZSW are about 2 to 10 kilogram, what they need in one batch. Larger coating lines need more than 40 kilograms, just as a pilot line production. And to get this large amount of materials in the required quality, you can go via the precursor route to these materials. This is a technically applied route. You make a continuous precipitation of a precursor, the so-called hydroxide, which is still free of any lithium. You have this powder, and in the second step, you put lithium to it, you heat it up in the presence of oxygen at high temperatures and end up with a final cathode active material. And I would show here in the 2 steps what you can reach with the precursor synthesis and what can be changed later in the thermal treatment. So the precursor synthesis allows you to grow particles and to control their morphology, and this is done in continuously run precipitation reactors. So the reaction equation is very easy. You precipitate the hydroxide just from the divalent metal with hydroxide, form a solid solution which you wash and dry and release and get the powder then. But this crystallization can be controlled very nicely. You can change the temperature, you can change the residence time of the materials in the reactor, you can change pH, you can change ammonia, which you need for that, the solid content. and by that have a very large field to optimize the crystallization process and control the particle size. And here just is shown a small design of experiments, changing temperature, pH, and ammonia here. And what we see is the SEM pictures you can obtain from these small parts. You see some of the pictures show really nicely spherical particles. Other of the pictures show more or less small grainy particles. And if you go beyond this scale, you reach even gel-type materials which you cannot filtrate anymore. So nothing which you can use then for technology. So, but the spherical shape or the shape of the materials is not all. There are some factors, for example, the tap density, which changes as well. And the tap density is more or less what you reach if you tap a material in a very often. How dense can you pack the spheres you obtain here? Yeah? And this tap density is an indicator on how much you can densify later the electrode. So the tap density is a function of particle size distribution. It's a factor of particle size density, of crystal density, and these can be controlled via precipitation. So the first both of them. Step 2, the lithiation. Here we can control size and shape of the primary crystals within these individual particles. The reaction is a thermal conversion of the hydroxide to the final product, here as well, LMNO. You put lithium hydroxide to it, oxygen, the hydroxide, and end up with a final cathode active material at 700 to 800 degrees. You can change the temperature here, temperature profile, gas atmosphere, and time of exposure. And just changing the temperature directly shows here in the single particles which came from the same precursor that you can optimize or increase the crystal size within the particles drastically. Here you see it in the cross-sectional view very nicely below. And this, of course, has an influence on different things, on density, on surface, on side reactions. Here's something on the powder conductivity we measured for these types of materials, so it drastically goes up for the materials made at higher temperature. And this is, of course, important for the rate capability to have good conducting materials. On the other hand, you can take further measures for stabilizing. You can go to protective coatings. And I just would like to compare the effect of crystallite size and protective coatings here. So what you see here in a coin full cell setup against graphite in a standard not stabilized electrolyte. What is shown here for a normal material which is uncoated, the black line, a 19 nanometer primary crystallite size material, we can reach about 100 cycles until we reach the end of life criterium at 80% of the initial charge. If we then coat this material with 0.5% boron oxides, same material, we can extend here the red curve, the capacity and the stability by the factor of 2.5. And if we then increase the crystallite size from 90 to 240 nanometers, coated with silicon, you can extend the stability even at the factor of 8. And this material is highly stable, has a fast discharge kinetics. Yeah, and as we can see in the capacity derivation curves here on the right-hand side, all changes happening on the positive or negative electrode in terms of aging change the profile. And this is highly pronounced at the lower curve for the strongly aging material or strongly aging cell. And we see for the stabilized cell, the green part, that nothing changes over several hundred cycles. So we can say neither the cathode nor the anode ages drastically in these optimized cathode materials. So particle design strongly influences performance of the material itself and life of the materials, but now we go a step further. What is if we handle this material in the processing? Here we have to take the material, we have to mix it, we have to coat it, we have larger mixtures. If we take a new material on a kilogram, gone? Okay. So we have to develop recipes for that. And I would focus here in the line of the mixing, of the coating, and finally densification of the electrodes, just on the mixing and the densification, just to show the influence of particle morphology on both factors. Starting with mixing and coating, so particle size and shape influence the solvent's amount you need in mixing. You can see it here for a nanomaterial and a spherical polycrystalline material. Both are lithium iron phosphates. Both have been mixed with the same recipe, same solvent amount, and we see the viscosity. So of the nanomaterial, the orange lineage is much higher compared to the spherical polycrystalline material. And this means to reach optimum coating viscosity, you need to dilute it much more than the other material. Use more solvent, you need more drying energy, you need to coat thicker layers, so there is a large influence on the coating behavior and the effectivity of the cost. On the other hand, if you go to densification, you densify the electrode and press out the porosity between the particles to get more materials into a cell. Yeah? So you can compress only the porosity which is between the particles. But there's as well an internal particle porosity. Yeah? So this is what I showed for the tap density of the material. And if we calculate just here for a dense material the theoretical capacity for a 20% porous electrodes and go up with 5% internal porosity, 10%, we see that the density of the electrode goes down, which means we get less of the material in a cell of a given volume. And in addition, you have more porosity to fill with the expensive electrolyte. So you have lower energy density at higher cost. So this plays a role as well, which is very important. So processing is influenced. But at this point, I want to step back in the lab. So there are many lab materials made, and it's very important to have these materials made. But the step, if you go from the lab to a material which we can really coat on a larger scale, is long. I just show it here for a single crystalline high voltage spinel. If we follow the typical recipes, you mix nitrates of the manganese and nickel compounds. You mix them with a 30-fold extent of a eutectic melt of lithium chloride, potassium chloride, heat it up at 900 degrees, let it cool down to a solid block. Then you wash it and dry it and end up with nicely shaped octahedra, which you can investigate. So this material or these routes are very good to get general information about the scientific background. How does this material work? What is needed to improve a material? But if we then want to make this material in a larger amount to make real cells, we end up, let's say, that it's not possible. Just taking a calculation for 1 ton of high voltage spinel made after this recipe would need 2 tons of educts, it would need 19 tons of lithium chloride and potassium chloride, and later it would need minimum 36 tons of water to wash out the lithium chloride and potassium chloride as well. It's quite a lot. In addition, you produce a lot of nitric oxygen, which you have to release somehow or to get rid of. And what we see here is the capacity curves, the blue one with the original recipe, and if we try to reduce the amount of this unwanted lithium chloride, potassium chloride, we see that capacity and performance go down drastically. So this is not the way to make the material better or to make it in large amounts, and we see even 1 kilogram is impossible to make in a lab scale. And we can go to alternative routes, so this is possible, but we have to change this. And so we developed a route which we'll publish soon. We take 1 ton of LMNS and we can go with 0.3 ton additive and 0.6 ton washing water very easily to more than 1 kilogram in our scale. So this was just to show the way is not too easy. If we have new materials from lab development, they have a long way to go before they can be used in technical applications. We see that particle design is an essential step in this process, and this particle design on the one hand strongly influences the performance and the lifetime of a material, but on the other hand, these morphological factors determine the processability of the materials along the whole value chain, from coating, calendaring, and drying, and manufacture in the end. So, and if we then want to go into the classification of the material in an industrial standard cell, we need really large amount of materials, and scale up of these materials is then a mandatory step. And this is what we are going to do very soon at CSSW. We build up a synthesis pilot line. This will be operative in 2025. And here we want to go to cathode materials design and production from the 1, 10 to the 50 kilogram scales. We want to close here the gap we've seen between lab and technical research, and we do it in a fully digitalized approach between manufacturing, analytics, and electrochemistry. And with this, I would close my talk. I thank you. I thank for funding to the Federal Ministry of Education and Research for projects, and I thank the organization committee for inviting me. And finally, I thank the group which worked hardly on all this. Thank you.
And thank you very much. So now we finished our presentation. Then we are gonna have 10 minutes break. And since it's so, we will have break until 5:40. Then we will have short panel discussion and Q&A session, since we have some delays from starting. Thank you.
I think the room is complete. Maybe we could start. The dinner is waiting for us. So my name is Juan Lee. I would moderate this session. So this session is about the panel discussion. I think I'm looking for my presenter. So I would like to actually just show you 2 slides before we move on to the panel discussion. So today we have discussed a lot, but this slide is actually one of the slides I just stole from the report called Alternative Battery Technologies Roadmap 2030 Plus from Fraunhofer ISE. So it's kind of expert's opinion. So, but I'm not saying that this is true. But I wanted to show you there are many different types of batteries, and there are many different types of applications. From the right-hand side, you could see 2- and 3-wheelers, light vehicles, cars, heavy vehicles, drones, eVTOLs, like those aviation applications that we've discussed also today. And today we have the speakers from different countries, from different backgrounds. Actually, it should just generalize a lot. So battery research has a similar pattern here. So there are fundamental levels of research where the chemistry defines the battery systems, also in part the physics. As today Mauro explained a lot intensively in terms of a new chemistry introduced with the lithium magnesium alloying, for instance. In case of material level, there we need new materials, and the materials could be redefined like Naoki, like Kazu introduced like ionic liquid systems. The new ionic liquid system would then bring the different key performances of battery systems. Also, Mogets today introduced about their carbon innovations. The materials are known, but they must be produced in a way that there will be different applications fulfilling all the KPIs of the different customers' demands that covers the activities also of the production level. In the cell level, the carbon could be also used as a different function, like working as a protective layer in all solid battery systems like Mogets introduced today. Also, some of the like foils, polymer foils introduced in the lithium sulfur applications to enhance the performances. So I see those kind of fields are actually, from the left-hand side, more academic-driven research. On the right-hand side, it's more about industrial-driven research. Where the industrial-driven research is going on, then there will be increased public awareness. So we see actually there, through the innovations and disruptions from those different areas of the research from the lab, different opportunities to sustain their future. But ever since we have the innovations and disruptions, soon there will be challenges. So I would like to use this session to actually use our event, which is the BrainLink X Lab, to bring the insights of how those opportunities are made through the innovations disruptions, and what are the current challenges are, and how could we resolve that. Also, one of the things we have to mention that like public receptions of battery innovations, or our common inceptions of the innovations are like price, power, maximum distance, and safety and longevity. But there are also sustainability we have to consider, like abundance of the raw material that today the expert mentioned about, or recyclability, and the environmental impacts also, which is aligned with what Peter today explained about the synthesis material where tons of water should be used. So in that regard, our topic, the title of our event actually called the Battery Innovation for E-Mobility, for Sustainable E-Mobility. So I would like to refresh this topic into mind, and I would invite the panel speakers to the ground. Please have a seat in front, and then we'll discuss different topics, and also the questions from the list that we have collected today. Hopefully seats are comfortable for you, everyone. I have several questions collected from the platform that Hyun-sang prepared today through the Menti. The first topic I would like to discuss is about the current challenges of the all-solid battery systems, and the question goes to Maura. Will that be okay that we'll break the formality and just call each other from?
Absolutely.
Yeah. So the question goes, there are challenges which could arise from the cost or safety. You mentioned that the all-solid batteries are generally safe, but is it generally safe once the different alkali metals could be innovatively introduced, like magnesium or sodium, lithium? So would you generally comment on the question, the limitations regarding the cost or the safety, etc., and solutions also combined with your presentations that you presented through the innovation?
Well, that's a lot of questions in a single question. Let me tackle maybe the motivation, and then maybe we'll discuss the other ones, right? You know, to me, I think we need to be very pragmatic. Whatever chemistry we're looking at right now needs to be superior or provide an advantage of the LFP chemistry that have been shown earlier. So we need to acknowledge the reality. You have batteries with less than $50 per kilowatt hour now available. So I think we should focus our attention on chemistry that could provide a competitive advantage over lithium ion, and that's where solid state can come in. It's also so early stage that some of the problems that we're now facing with lithium ion we can tackle from the ground up. So you're mentioning recycling earlier. So you can consider or include designing principle to facilitate recycling down the road if you design the chemistry from scratch, why it's very difficult to then backtrack on 30 years of development in lithium ion space to do that. For example, what polymers you decide to use in your cathode side. There's regulation coming in from Europe right now. We need to ban fluorinated polymers. So you can think about moving on from fluorine now that we're still quite early on in the development. You can think about what solid electrolyte you use and how you can actually recycle them more efficiently. So in that sense, I think designing a new battery from scratch could be beneficial. Then you were mentioning safety. Safety is it's another can of worms altogether. Is it safer than a liquid electrolyte battery? Lithium, if you will need to implement metallic lithium in both liquid and solid, then I would say yes. Then comparing a safety of a lithium metal battery with anything that is not lithium metal, that is problematic. The very low melting point is a big problem. If you end up with some sort of a parasitic reaction that raises the temperature and results in melting your lithium, you're going to have to deal with something extremely problematic. And that is something that I think some of the people that are working on solid state are testing right now, doing nail penetration tests, see how a lithium-ion battery reacts. Ultimately, the more energy you store in your battery, the more problematic it would be in the event of a thermal runaway or a safety event. But it's something, again, that we can design from the ground up, but I think it's a unique opportunity. Now, you were mentioning different potential negative electrodes, different metallic electrodes. Well, you need to be aware of the limitations. We use lithium for a reason. It moves quite rapidly in solids, in particular in cathodes as well. And that's a big advantage. And also, you need to be considering also what advantage it would provide, for example, a sodium metal negative electrode. If you're talking about safety, something that melts at a little lower temperature, that would be even more problematic. So I think we need to be very cold in a way in what chemistries we pick, what the problems are, tackling them in as smarter scientific way as possible, but from a fundamental science and also engineering side, and then maybe be more aware of the designing principle from the ground up if we can. So hopefully that answers your question. I think it's a long answer.
Yes, I think your memories are quite impressive, though. But maybe one question in that regard. So, knowing those of the industry standard of the safety and the direction we have to go, from some of your researches or innovations or options, the innovations you made, how could your innovation from fundamental side could we resolve some of them?
You say, how do you then go from fundamental science to actual impact? Mm-hmm. I mean, that's a challenging one. I think we're having conversation about that earlier. I'm talking about Europe in general. I think in general we're quite leading in terms of like fundamental science, and I think we've been quite, I wouldn't say bad, but not as efficient in translating this fundamental understanding into industries. I think we're noticing a lot of cases right now. If you follow the news, if you're in the battery business, we're talking about Norfolk, for example, which is quite an interesting example of trying to build manufacturing in Europe from the ground up. Mm-hmm. It is extremely capital intensive. It requires a lot of patience. It requires help, from governments as well, which is something, we need to deal with to a certain extent. So I think, there is an element of doing the science. When you get to a certain level, you want to scale it up, then it's about, the economics of it. And I think that's something that we need to improve. I'm talking about the European side, while if you can look at the Chinese side, for example, it's been extremely successful in doing so. Mm-hmm. If you look at what CATL did in the past 10 years, it's actually unheard of. So I think it becomes more in the realm of geopolitics. I think if we're more knowledgeable of what it takes to scale a technology up as fundamental researchers, that would be beneficial. So make sure that when we're looking at novel chemistries, novel problem, we look at them also with the lens of what would you then need to do to scale it up? Mm-hmm. Or how can you actually manufacture this? So engage with industry, for us, I think it's very important. And I love to do that personally, because I really like to wake up in the morning and feel like whatever I do could make an impact at some point, mm-hmm. but it's not only about us. I think that's, goes to a certain level. I make sure that we work on relevant problems and make sure that we have good context with industry as well. That's maybe my answer to your question.
Yeah, thanks a lot for your valuable comments. I think I would like to stick to the topic that you just brought, to being competitive against the Asian markets, etc. From the fundamental levels you mentioned, maybe we move on to a step further to the material level. And also it aligns also with the discussion that Egbert brought today. So my question continues with Egbert. So based on also the comments that Mauro made, you mentioned a lot about the raw materials, independency, etc. So under the current situation, the raw materials in general will be a lot cheaper in China or Asia. How could Europe, from the research and innovation side, could bring the competitiveness back to Europe?
Hello? Yeah, it's state controlled. It's they can live with very low margins where European or US or Korean companies maybe not be able to work with. So on a pure economic level, it's next to impossible, I would say. So you would need to implement other parameters like CO2 footprint, also recyclability. You would also fluorine-free chemistry, all these things, because also in Europe there are new regulations regarding fluorine chemistry. So we cannot work with it anymore, but it is imported in the batteries. So that's kind of brings an absurd situation. So this, where on the regulation part can be done a lot to, let's say, level the competition.
I think I do really agree in that aspect. But possibly there could be some brilliant disruptions coming from the innovative material side. I remember the protective layer which was implied in also the battery that Moritz showed. So this is like a small percentage of the material that has been driven by non-Asian company. In that regard, I would like to continue the discussion with Moritz from Northern Graphite, how these disruption innovations could make this non-Asian market situation more independent and more competitive.
Well, I think in general, these kind of innovations and bringing it also to the application can definitely help to maybe jump over one generation, like we have seen before. Classical all-solid-state battery starts with a lithium metal anode, and then if you go directly to a lithium metal free system where you say, okay, we can save some of the precious lithium, and we go to a more, let's say, affordable and abundant carbon system, it can help to accelerate. At the same time, it's also a challenge to get this through the product chain, get it into the market, since for sure there's only a very few players in the end who have also the know-how, mainly in Asia, to drive these kind of battery chemistry and battery systems to a final product.
All right. I was thinking of the sulfide or like oxygen oxide-based like anode systems. Are there? I'm going more details to your product that you mentioned, because I see that your product is really unique. I don't see elsewhere about this unique feature that you introduce. Are there any progresses that they could like beat the facts of those price matters or any regulations? I mean, beating the situation by the product's unique selling point in terms of more detailed applications of like sulfide and oxide applications of also the battery systems.
Yeah, I think the challenge here lies in the majority of the systems. What we see in the market at the moment, that it seems that especially the sulfide systems are a little bit more mature and have more tractions, and might be also the first, let's say, real all-solid-state battery systems in the market. With oxide systems, where this carbon approach would also work, so like an anode-free design works also in an oxide-based system, but there we see the challenge, especially on the solid electrolyte part, getting the oxide electrolyte in the quality, and also then for sure in the next step in the quantity required. And I think overall it links a little bit in the challenge how to transfer very good results on a small scale in the lab to products which are then produced on a large scale. And then again, the question is who brings the know-how and the capability to make this scaling effect? And I think that will be a challenging question again. And again, we just had the topic with China. Also there they have a huge advantage, or like a huge expertise in terms of scaling new technologies very fast. And in the end, also the market needs to see with the all-solid-state battery, if the Korean, the Japanese, the European, the US market wants to play there an important role, or again, if they just wait that someone else is doing the hard work and brings it to the masses and also reduces the cost.
All right. About the cost, and also on the top of what you just mentioned about bringing the lab material to the product, actually Peter showed a good use case of how the synthesis step must be optimized to bring the synthesis into rather sustainable way. I think there will be lots of from Peter could say what are the most challenging steps from your pilot plan. I know there are many challenges, but make it like stepwise. The most important challenges. How one could deal with that?
That's the good question. So we have to start with maybe a promising lab material just to see and think about, can this produced in a larger scale at all, or do we have to think about different ways to reach the intended morphology, structure, chemical composition, and finally electrochemical activity. So we have, of course, the typical production line, which is used for the cathode materials in our labs. So from the precipitation to the thermal treatment and afterwards the refining. But we have to learn for each step. It's all over about 14 single steps, and each of these steps is really critical with respect to the quality of the final material. So we have to optimize in all steps. And this can be done in smaller scale, maybe in a 1 liter reactor or something. But then to maximize the output with design of experiments and see which morphology is best for this specific type and crystal structure, and then go into the next steps to make larger materials. I think mostly important is that you have the chance to have enough material to prove it in some industrial kind of cell type. For this you need materials with a nice homogeneity, so this is important. A lot of exchange is needed between lab and, let's say, these intermediate steps to see how we can merge together the experiences of lab and small scale up to find a way to this. This cannot be done independently, to my opinion.
Yeah, you just mentioned like 40 different parameters, but that is just for synthesis process. There will be the mixing steps and calendaring steps, etc. And there will be multiple parameters accumulating.
Yes.
So I see that digitalization will be very much important. You just mentioned last time about digitalization. So what do you think about the status of like the kind of high level of digitalization in academia?
Please again, the last.
What's the status of like digitalization in general in European like academic research area?
Yeah. So in Germany we have, let's say, the material development. We have cell development. This has been funded in larger projects and different, let's say, really pilot plant scales. But the material what has been provided in the beginning was more or less a material which was not of any interest anymore. So the material from industry was not of the highest quality. It was more or less something where they do not lose any knowledge to outside. Yeah. And I think it's very important to do this development of cells with the highest performance materials you can reach. Because as we see, if we go to nickel-rich materials, we have different processing behavior. You have gassing in the cells. So it's completely different from what has been developed, let's say, on a standard material. So we need to go to high-performance materials to see how they behave in later pilot line production and how they behave in cell, how they are processable. And at the moment the funding situation is, let's say, quite limited in Germany. So this is since 1 year, but we have to see how to control. And I think academia can support with new ideas the industry. We can be in between, more or less, going to larger scales, but at least collaboration is needed very intensely. So this is my opinion.
About the high performance material, thanks, Peter. I would like to give a chance now to Naoki, because you've talked a lot and showed the recent results as well about the high capacity materials. They are believed to be high capacity performing materials. Are there any general challenges you could you could explain to the general public, and also the current solutions to that? That's one part of the question. And second question would be, are you having a good industrial and R&D research environment in Japan?
Okay, so now my next step is some discrepancy between the commercial application and basic research is actually, I think, loading over materials. Typically, people use a more small loading, so may thinner electrode for material evaluation. And then, of course, if we make such a thinner electrode with less loading, we can make good publications. But a practical application is completely different. So aerial capacity is also heavier loading. So situation is completely different. So now, therefore, I think a more important point is now, so stages rather than material level is our target is a commercial application, meaning a more heavier loading, small amount of carbons, high aerial capacity. So of course, very tough challenges, but such a criteria, parameter is also very, very important. So R&D in Japan is actually, so we have many battery companies as well as car companies. So I also have many collaborations with these companies. So, and also funding situation for such a company is, I think really nice. For example, Panasonic is they are trying to maybe 1,000 researchers for research development. So and also they are more focusing on battery. So R&D situation is really nice. However, now problem is resources for persons. So number of student population is now going down. Student number is also going down. So problem is resources of human resources is a problem in Japan.
I think this is like general in the world that the battery resources are more driven by the industry.
Yes, too rapid expansion.
Yeah. And I think in that regard, it's really important to bring the disruptions, innovations, really from the lab, having good interaction with industries. In that regard, the disruption you brought today about high concentrate system, are you receiving good feedback from the industry whenever you approach that?
Yeah. Always industrially so complaining me about high viscosity. Yeah, but now we are trying to make more to solve this problem. So viscosity problem will be solved. However, cost problem. This is a very difficult point. So salt cost, especially lithium FSA, is very, very expensive. So, but anyway, so mass production means cost of a material is gradually decreases. It's a history. Maybe we can reduce its cost. If we can make some highly concentrated applications, is used for commercial applications.
Please deliver this comment from the company to Egbert.
Yeah. I'm already trying.
Yeah. And stick to the cost of the disruptions. So Katsu, you show many of the different applications when ionic liquids could be applied. I think this question will be the same. Many people will argue about the price. Would you also comment on that? Also, if you have received sufficient feedback from the industry.
Yeah, as Yabuchi-sensei said, generally salt is more expensive than solvent, and if we go to ionic liquid is the extreme case, so it's just salt. And then we have metal salt and organic salt, but organic salt is usually quite expensive. So if we want to use ionic liquids, we always have that problem. But regarding the safety, ionic liquids have some advantages, obviously. So even with we always have to test with the charged materials, but still ionic liquids. We did a lot for sodium-ion batteries before with companies, and then a lot of tests gave us a better result for ionic liquids compared to organic solvents. So it's always, if you take this and then you lose this, like that way. So of course, ionic liquids are more expensive, but if you take safety, or you can also mix them to get better ways from both sides. So it's always like that, I guess.
I think that's a good point to counter-argue with the unique selling point, like you just mentioned, the safety and other factors that could cover up the cost. Thanks a lot for your valuable comments. We have also discussed different types of all-solid battery system and with the sulfur chemistry. So my question goes to Georg, because I've known the lithium sulfur system for a long time. I would like to ask you, what are the general challenges that the lithium sulfur system is not quite broadly commercialized yet? But I think you showed the generally nice guideline of that this system could be used for the aviation applications. So would you generally summarize the challenges of this system and how then also the battery concept would help in that regard?
So, there are a number of challenges. As I mentioned, of course, the aerospace applications are highly regulated. We have very high safety demands. And still there is this quite predominant problem of the polysulfide shuttle that makes the capacity degrade over many cycles. Of course, you might think of, let's say, battery exchange might be a feasible concept also for aeroplanes. but still, of course, you need a number of cycles that run. In the aerospace industry, you always also have to have a, how do you say, let's say, a safety excess, kind of. So you need some percentage, of course, to make sure there is enough energy for the whole flight. And yeah, that means, I mean, we still have to tackle these issues. In terms of the capacity retention, there is some nice progress in the literature, but often there is a problem when you scale, when you go to other cell formats, you cannot really reproduce this. So we have to find solutions that really are, let's say, flexible and are reliable, that can also be implemented in an industrial fabrication later. And as mentioned, I mean, so far we are relying on the lithium anode, which is also a problem. It might be mitigated when going to solid state, but still it's an important issue. I have to say that we are still, let's say, rather in our research at the beginning when tackling some larger airplanes. There is also the question of thermal management that we are currently dealing with, the question of the architecture in the airplane. But no matter which technology you're actually, let's say, going to, there are still many issues to be resolved.
One more additional perspective, because I think if I remember correctly, some of the carbon materials are already applied in lithium surface system to reduce the redox shuttling. In that regard, so how do you like this kind of approach, that protective layer that was discussed today, that was introduced in the anode at also the battery system? Could it be then used in lithium surface system, then which could then prevent the redox shuttling at the same time to extend the cycle life against the dendrite formation, etc.?
It could be used. So I'm not convinced of all of the concepts that there are in literature currently, because I mean some of the sulfur dissolution is required so that the battery is working well. In fact, we have also been working on such a protective layer, but it was not having a, let's say, specific targeting interaction with the sulfur species. And this might be a solution. I mean, there are additives that people are using, or specific functional groups of such a protective layer that would, let's say, couple and then prevent a diffusion of the sulfur. This is also an interesting concept that we are actually currently further pursuing.
Yeah, I brought this question on purpose because, you know, in the panelists, you know who to talk with now. And because that's the network, and that's the benefit of really the networking. In that regard, this event I see is a very successful event. I really appreciate the Korean government to support us. I think we will discuss a lot longer. I have tons of questions. I think it would be also nice that we could have a free discussions today, but today the time is limited. I think you are quite hungry. So I would like to wrap up the session with that. And thanks a lot for coming out and share your thoughts and having a successful and fruitful discussions today. I will give my microphone to the organizer.
Yeah. So now we have another participant from Austria, Professor Stefano Passerini. And he just arrived to South Korea, so maybe he's very tired. And now we are gonna have a photo session. So we are going to take photos and we go to the dinner.